In 1952, a Japanese research vessel sailed into a stretch of the Pacific Ocean and was never seen again. 31 people, no distress call, no wreckage, no fuel slick on the surface, no life jacket, nothing. The ocean returned not a single piece of evidence that the ship had ever been there at all. That alone would be enough to make this place worth knowing about. But that ship was not the beginning of this story. It was the moment the Japanese government ran out of ways to ignore it. Japanese sailors had been calling this water Ma-no Umi for centuries, the Devil's Sea, and the name did not come from folklore. It came from the counting, from the ships that left port and the ships that did not return, from harbors that kept waiting for vessels the sea had already decided were not coming back. Ships here do not always sink the way ships are supposed to sink. The ocean simply just closes over them as if nothing had been there at all. While the Bermuda Triangle became a global legend, the Devil's Sea remained almost unknown outside Japan, despite having a far stronger scientific case for genuine danger than the Bermuda Triangle has ever been able to match. The question is not whether this place is dangerous. The question is why, and the answer, when scientists finally started finding it, turned out to be stranger than the legend ever was. So tonight, we are descending into one of the most violent stretches of ocean on Earth to understand why this sea earned its reputation long before modern science could explain what was happening beneath it. But before we do, let me know in the comments, what part of the world are you watching from, and is it day or night there right now? If you enjoy calm videos like this, please give this one a like and maybe subscribe. Now, let's begin. Far out in the western Pacific, beyond the crowded ports and industrial coastlines of modern Japan, the ocean begins to widen into something quieter and far older. Cargo routes thin into long blue corridors. Fishing boats become distant specks against immense water. Southeast of the Japanese mainland, between the Ryukyu Islands and the Ogasawara archipelago, there lies a stretch of sea occupying a narrow band between roughly 25 and 35 degrees north latitude, a corridor threaded through the greater Pacific like a dark current hidden inside a larger body. Ships have crossed these waters for centuries, following trade winds, seasonal migrations of fish, and the invisible pathways that connected island communities long before modern maps existed. To many outside Japan, the place barely exists in cultural memory. The Bermuda Triangle entered Western imagination through magazines, television documentaries, and best-selling paperbacks, eventually becoming a permanent piece of popular folklore. The Devil's Sea never received the same attention. Charles Berlitz, whose 1970s writing transformed the Atlantic mystery into a global obsession, mentioned the Dragon's Triangle only briefly, treating it as a distant Pacific counterpart before returning his attention westward. The imbalance was not created by evidence. It was created by language, geography, and publishing. Most records connected to the Devil's Sea remained locked inside Japanese archives, maritime reports, fishing records, and local oral traditions that rarely crossed into English translation. Yet the history surrounding this water reaches much deeper than the modern era. Japanese accounts describing strange disappearances and dangerous currents stretch back to the 12th century, preserved through generations of sailors who learned to read the moods of the Pacific with careful attention. Fishing communities along the Izu Peninsula carried quiet rituals into their departures, stopping at shrines before entering the corridor, offering prayers to sea spirits, timing voyages around seasonal patterns remembered through experience rather than instruments. Beneath the spiritual language existed something practical and inherited. Certain waters behaved unpredictably. Certain seasons returned with unusual violence. Boats vanished often enough for caution to become tradition. After the Second World War, those old fears collided with a modern national crisis. Japan's recovery depended heavily on maritime trade. Shipping lanes carried fuel, food, machinery, and raw materials essential to rebuilding cities, still scarred by bombing and economic collapse. The ocean was not simply part of the nation's geography, it was the bloodstream of recovery itself. When vessels began disappearing in the waters southeast of Tokyo during the early 1950s, the consequences extended far beyond rumor or superstition. Every lost ship represented cargo delays, financial damage, and growing uncertainty inside a country already struggling to rebuild stability from ruin. The response from the Japanese government reflected that seriousness. Investigations were funded formally through scientific and maritime agencies, involving researchers, oceanographers, and naval specialists attempting to understand why vessels were vanishing inside the same corridor. The dispatching of the Kaiomaru No. 5 was not an act of folklore chasing fantasy. It was a state-supported research mission equipped with instruments and personnel meant to produce measurable answers. The disappearance of that vessel deepened the sense that something within this region resisted ordinary explanation, though the true difficulty lay not in superstition, but in the sea itself. The Pacific floor beneath the Devil's Sea descends into enormous depths shaped by volcanic ridges, trenches, unstable slopes, and constantly shifting geological structures. For much of the 20th century, humanity simply lacked the tools required to study such terrain properly. Surface ships could map only fragments. Sonar technology remained limited. Deep-diving submersibles capable of reaching the abyssal environment did not become sophisticated enough until the late 20th century, and even then, exploration moved slowly through darkness, pressure, and distance almost impossible to imagine from land. For centuries, sailors crossed above forces they could not see, recording only the consequences that reached the surface. Beneath the shipping lanes and weather systems of the Western Pacific, the Earth itself is moving, not with the slow stillness suggested by continents on a map, but with immense pressure unfolding continuously beneath the ocean floor, deep below the reach of sunlight or anchors. The Devil's Sea rests above one of the most active regions within the Pacific Ring of Fire, a vast horseshoe-shaped chain extending roughly 40,000 kilometers around the edges of the Pacific Basin. Nearly all of the planet's strongest earthquakes originate somewhere along this immense boundary, where the outer shell of the Earth remains in constant motion beneath the sea. The crust of the planet is not a single unbroken surface. It is divided into enormous slabs of rock called tectonic plates, each drifting slowly across the softer mantle below. Their movement is measured in centimeters across years, gentle enough to seem motionless within a human lifetime, yet relentless over geological time. Along certain boundaries, plates slide past one another quietly. In other places, they collide with extraordinary force. The Devil's Sea lies above one of those collisions, where the Pacific Plate, the Philippine Sea Plate, and the Eurasian Plate converge within close proximity beneath the Western Pacific. Far below the surface, one plate bends and sinks beneath another in a process known as subduction. Rock descends into deeper regions of the Earth where pressure and temperature rise steadily, while the overlying crust strains against the movement below. This is not a calm or stable arrangement. The seafloor across this region exists in a state of continual stress, as if the planet itself is slowly tightening and releasing muscles hidden beneath kilometers of water and sediment. Pressure accumulates silently for years, sometimes centuries, before releasing in moments that reshape coastlines and send energy rippling through entire oceans. Subduction zones produce the most powerful earthquakes known on Earth. The greatest seismic events in recorded history have emerged from these boundaries, where entire sections of crust suddenly slip after long periods of resistance. In the waters northeast of the Devil's Sea, a nearby section of this same tectonic system ruptured in 2011 during the Tohoku earthquake, the most powerful earthquake ever recorded in Japan. Instruments measured the event at magnitude 9.1, a scale of force almost impossible to grasp directly. The amount of energy released during those few minutes has been compared to hundreds of millions of Hiroshima bombs, though even comparisons like that struggle to contain the reality of geological energy unfolding beneath the sea. Along the Japanese coast, cities shook, seawalls failed, and the Fukushima disaster began unfolding in the aftermath. Yet out in the open Pacific, above the deeper sections of the subduction zone, the rupture itself remained invisible. The ocean surface gave almost no warning before the forces below transformed the water above. This remains one of the unsettling realities of the Devil's Sea corridor. The violence responsible for shaping the region originates far beneath ordinary human perception. A ship crossing overhead may encounter calm skies, steady currents, and clear visibility, while pressure accumulates silently in darkness thousands of meters below. Underwater earthquakes within this zone occur without regard for shipping routes or seasons. Some release only minor tremors. Others shift enormous sections of seafloor in seconds. Unlike storms forming gradually across weather maps, seismic events do not announce themselves in ways surface vessels can easily interpret. Foreshocks are inconsistent. Stress patterns remain difficult to predict precisely, even with modern monitoring networks. For sailors above, the first indication of change may arrive only after the energy has already entered the water column. The Devil's Sea exists inside a living geological engine, one that has been operating for tens of millions of years beneath the Pacific. The islands surrounding Japan were shaped by these collisions. Trenches were carved by them. Volcanoes rose because of them. Even now, beneath the black water and the movement of the currents, the earth continues pressing against itself in darkness, slowly rearranging the floor of the ocean below every passing voyage. Far below the passing hulls of cargo ships and fishing vessels, mountains are rising in darkness. They do not appear on the horizon because most of them never break the surface. Hidden beneath kilometers of Pacific water, the Devil's Sea contains one of the densest concentrations of submarine volcanoes anywhere on Earth, a scattered volcanic province spread across the unstable floor of the western Pacific. Some rise thousands of meters from the abyss below. Others remain low ridges, venting heat and gas quietly into the surrounding sea. Many are still active, their eruptions unfolding far from human sight beneath the pressure of the deep ocean. Unlike the volcanoes familiar on land, submarine volcanoes rarely announce themselves with towering columns of ash visible from distant coastlines. Their violence occurs inside water itself. Magma encounters seawater under immense pressure, releasing bursts of steam, volcanic gas, shattered rock, and superheated fluid into the surrounding ocean. Entire sections of seafloor can fracture open without warning, creating eruptions that reshape underwater ridges and seamounts silently beneath the surface world above. One of these volcanoes carries a name that became inseparable from the history of the Devil's Sea. Myojin-sho lays south of Tokyo, within the same corridor where vessels had been disappearing during the early 1950s. In September of 1952, the volcano entered a violent eruptive phase, throwing steam and volcanic material high enough to be observed from passing ships and aircraft. Japanese authorities dispatched the Kaio Maru Number 5 specifically to investigate the eruption, carrying scientists, researchers, and crew tasked with studying the strange activity rising from the sea. The vessel reached the area while Myojin Sho remained unstable beneath the water. Then, without surviving witnesses or distress transmissions, the ship vanished. Weeks later, fragments of debris were recovered, drifting near the eruption zone. Modern analysis of those findings, combined with geological surveys of the region, led researchers toward the explanation now considered most credible. The Kaio Maru Number 5 had likely been destroyed by the volcanic event it was sent to study. An underwater eruption affects far more than the seafloor itself. Volcanic vents release immense quantities of heated gas into the surrounding water column, including carbon dioxide, sulfur compounds, and steam rising violently upward through the ocean. Ash and fragmented rock churn through the water, while pressure waves travel outward beneath the surface. In certain conditions, the water directly above the eruption can become saturated with gas bubbles dense enough to alter the physical behavior of the sea itself. Ships float because seawater possesses enough density to support their weight, but water filled heavily with volcanic gas behaves differently. The mixture becomes lighter, less capable of generating buoyancy beneath a vessel's hull. Oceanographers refer to this phenomenon as a density reduction event. Within such a zone, a ship may lose support almost instantly. Instead of flooding gradually or listing over time, the vessel can drop downward abruptly as the surrounding water ceases behaving like normal seawater. For crews above, the transition would unfold with terrifying speed, though the ocean itself would reveal little warning beforehand. No visible reef, no approaching storm line, no collision, only the sudden collapse of buoyancy beneath the hull, followed by violent turbulence and descending water carrying the vessel into darkness before radio operators could send a message or lifeboats could be lowered. The silence surrounding several disappearances in the Devil's Sea begins to look less mysterious when viewed through the behavior of erupting submarine volcanoes. The corridor contains more than 20 known submarine volcanoes, though mapping efforts continue, revealing additional formations hidden beneath the Pacific surface. Some remain dormant for centuries before reawakening. Others vent continuously through hydrothermal fissures, too deep for ordinary observation. Even now, research vessels moving through the region cross above structures that are still being charted in detail for the first time. The seafloor beneath the Devil's Sea is not fixed terrain. It is an active volcanic landscape still building itself in darkness, one eruption at a time. In the deepest parts of the ocean, there are places where fire and ice exist together, not the ice of drifting polar seas or mountain winters, but a stranger form created under immense pressure far below sunlight. Along the floor of the Devil's Sea, methane hydrates rest buried inside layers of sediment, pale crystalline structures where methane gas becomes trapped within frozen cages of water molecules. They resemble compacted ice, stable only within the cold temperatures and crushing pressures of the deep Pacific. Disturb those conditions, even briefly, and the structure begins to collapse. The seafloor beneath this corridor contains unusually rich hydrate deposits formed over long spans of geological time. Organic material drifting downward from the surface settles into sediment layers where microbial decay slowly generates methane gas. Above, kilometers of ocean create the pressure necessary to trap the gas inside hydrate crystals, while geothermal heat rising through the unstable crust below adds another layer of tension beneath the sediment. The result is a landscape holding vast reservoirs of compressed methane beneath the Pacific floor, suspended in a delicate balance between stability and release. Most of the time, those deposits remain sealed beneath mud and rock, hidden from the moving water above. But the Devil's Sea is not a stable environment. Earthquakes ripple through the crust. Submarine volcanoes disturb sediment layers. Pressure shifts travel through fault systems buried beneath the ocean floor. Under certain conditions, methane hydrates destabilize rapidly, releasing enormous quantities of gas upward through the sediment in violent bursts. When methane escapes from the seafloor at sufficient scale, it does not rise gently. The gas expands as it ascends through decreasing pressure, creating immense vertical plumes filled with bubbles racing toward the surface. Within these rising columns, seawater becomes heavily aerated, transformed into a turbulent mixture of liquid and gas. To the eye above, the ocean may appear strangely disturbed or unusually pale, though in rough weather the change could remain almost invisible beneath waves and spray. A vessel passing directly across such a plume encounters a problem rooted in simple physics. Ships float because seawater possesses enough density to support their mass. Replace a substantial portion of that water with methane bubbles, and the supporting density drops suddenly beneath the hull. The surrounding ocean no longer behaves as a stable surface. Instead, the ship begins sinking into water that can no longer carry its weight. Laboratory experiments and marine engineering simulations have demonstrated how rapidly this process unfolds. In controlled models, vessels entering concentrated gas plumes lose buoyancy almost immediately. Large sections of the hull descend unevenly while turbulent water strips away stability. Under extreme conditions, a ship can disappear beneath the surface in less than 30 seconds, faster than crew members could organize evacuation procedures or send coherent distress calls. Radios require moments. Lifeboats require preparation. A methane blowout removes those moments almost entirely. This possibility reshaped the way researchers interpreted several disappearances associated with the Devil's Sea. Investigators examining the vanished vessels noticed a recurring absence of ordinary evidence. No extended radio transmissions, no scattered life rafts drifting across search zones, no widening oil slicks reflecting sunlight from the surface. In some cases, ships appeared to vanish between scheduled communications, as though the sea had closed over them almost instantly. The mechanism itself is not theoretical fantasy. In 2004, a major methane blowout occurred off the northwest shelf of Australia, powerful enough to be observed from satellites orbiting high above the Earth. Gas erupted through the ocean in volumes so large that the disturbance altered the appearance of the sea surface across a broad region. Yet that section of Australia's continental shelf is considered geologically calm compared with the unstable volcanic and tectonic systems beneath the Devil's Sea. Deep beneath the Pacific corridor, methane remains locked inside frozen sediment even now, waiting beneath pressure and darkness in one of the most geologically restless regions on the planet. Long before satellites crossed overhead and digital navigation systems stitched the oceans into glowing grids, sailors moved across the Pacific by trusting a small trembling needle suspended inside a compass housing. In open water, far beyond visible coastlines, that needle became a substitute for land itself. It offered direction where no roads existed, guiding wooden fishing vessels, merchant ships, and naval convoys through weather, darkness, and immense distance. In the Devil's Sea, however, mariners learned that the needle could not always be trusted. Japanese sailing records from the Edo period contain repeated references to strange navigational behavior within these waters. Compasses drifting unexpectedly, bearings shifting between repeated measurements. Courses that appeared correct on instruments but slowly carried vessels away from intended routes. Sailors described the sensation of moving through water that resisted ordinary navigation, where familiar methods sometimes produced contradictory results. The language varied across centuries, shaped by local traditions and maritime vocabulary, yet the underlying pattern remained strangely consistent. Modern scientific surveys eventually confirmed that the region does contain measurable magnetic anomalies. These are localized areas where the Earth's magnetic field behaves irregularly compared with surrounding sections of ocean. The cause lies deep beneath the surface, woven into the same geological instability shaping the corridor itself. Volcanic activity and tectonic movement continuously alter the composition of the sea floor, creating a submerged landscape filled with rocks carrying different magnetic properties. When molten basalt rises from beneath the crust during submarine eruptions, it cools gradually inside the surrounding ocean. As the rock solidifies, iron-bearing minerals within it align with the Earth's magnetic field at that exact moment in geological time. The orientation becomes locked into the stone itself, like a frozen imprint of the planet's magnetic state. In stable regions, these magnetic signatures remain relatively uniform across broad areas of sea floor. But the Devil's Sea is not stable terrain. New eruptions occur beside older volcanic formations created under different magnetic orientations, while tectonic shifts fracture and rearrange sections of crust continuously over millions of years. The result is a submerged patchwork of magnetic inconsistencies scattered beneath the Pacific corridor. One section of seafloor may pull subtly against a compass needle, while another nearby formation influences it differently. These variations are not dramatic enough to spin instruments wildly in circles as fictional stories sometimes imagine, but they are sufficient to create genuine navigational error, especially in earlier centuries, when ships relied heavily on magnetic bearings, combined with dead reckoning and celestial observation. A compass drifting even 15 degrees away from true north could become catastrophic in difficult weather. Far from coastlines, with storm clouds obscuring stars and no visible landmarks remaining, a small error compounds slowly across hours and days. A vessel, intending to avoid dangerous currents, could unknowingly move deeper into them. A captain attempting to steer clear of volcanic shallows might instead drift directly across unstable water. In ordinary conditions, crews could often correct such mistakes eventually. Inside the Devil's Sea corridor, where storms, currents, and geological hazards converged together, those lost margins became far more dangerous. Even modern navigation systems have not removed every uncertainty from the region. Contemporary vessels crossing certain sections of the corridor have occasionally reported irregularities in satellite positioning and electronic navigation signals, though the precise causes remain under active study. Some researchers suspect interactions involving ionospheric conditions, volcanic activity, or complex magnetic structures beneath the sea floor. The effects are usually temporary, subtle enough to avoid disaster aboard modern ships equipped with multiple redundant systems, yet their existence continues the long pattern recorded across centuries of Pacific navigation. This is one of the sharpest distinctions between the Devil's Sea and the mythology surrounding the Bermuda Triangle. Investigations into Atlantic magnetic anomaly claims have largely concluded that the Bermuda region behaves within expected navigational norms. Its compass variations are mapped carefully and understood scientifically. In the Western Pacific corridor, by contrast, the anomalies are measurable, geologically plausible, and supported by both historical observation and modern survey data. Beneath the surface of the Devil's Sea, the Earth continues reshaping its own magnetic memory through volcanic fire and shifting crust, subtly altering the invisible forces sailors once depended upon to find their way home. Across the western Pacific, there is a river moving through the ocean. It has no banks, no visible edges, and no sound distinguishable from the surrounding sea. Yet it carries more water than every river on Earth combined. Mariners along the Japanese coast named it the Kuroshio, the Black Current, after the deep indigo color it gives the surrounding water under certain light. Flowing northward from tropical latitudes, the current passes alongside the Devil's Sea in a broad stream of warm Pacific water, moving steadily through the corridor at speeds reaching roughly 3 knots. Farther east, colder currents descending through the North Pacific drift toward it from distant waters. Where these systems meet, the atmosphere above the ocean becomes unstable in subtle but powerful ways. Warm water transfers heat continuously into the air above, feeding rising moisture and disrupting pressure patterns across the open Pacific. The sea surface here stores enormous quantities of thermal energy, especially during late summer and early autumn when tropical heat accumulates across the western Pacific basin. In these conditions, storms begin quietly. A loose collection of thunderstorms gathers over warm water. Winds rotate weakly around a developing low-pressure center. Moisture rises higher into the atmosphere, condenses, releases latent heat, and feeds the circulation below. Over ordinary oceans, some systems weaken before fully organizing. Inside the Devil's Sea corridor, the environment often encourages the opposite. The water remains warm not only at the surface, but deep below it, meaning storms cannot easily churn up cooler water to weaken themselves. Heat remains available continuously beneath the rotating clouds. Meteorologists refer to sections of this region as a typhoon nursery, one of the primary birthplaces for tropical cyclones in the Pacific. Here, disorganized storm systems can intensify with astonishing speed. Winds strengthen, central pressure falls rapidly, spiral rain bands expand outward across hundreds of kilometers of ocean. In less than 2 days, a weak tropical disturbance can evolve into a fully developed super typhoon, carrying enough energy to rearrange entire coastlines. The Pacific produces some of the largest and most powerful storms on Earth precisely because of this deep reservoir of warm water. Atlantic hurricanes, though immense, often weaken more quickly when they disturb cooler layers beneath them. In the Western Pacific, storms sometimes continue feeding uninterrupted across broad regions of ocean heat, extending far below the surface. The Devil's Sea sits directly inside one of these energetic corridors where atmosphere and ocean exchange heat continuously beneath rotating cloud systems. In 1979, one of the most extreme examples formed within this wider region. Super Typhoon Tip expanded into the largest tropical cyclone ever recorded on Earth, stretching across approximately 2,220 kilometers of Pacific sky. Sustained winds exceeded 300 kilometers per hour near the storm's core, while the surrounding cloud shield spread across an area so vast that weather satellites captured it as a spiraling continent of cloud over the accessed ocean. Its formation path crossed through waters connected to the Devil's Sea corridor, drawing energy from the same unstable Pacific environment that continues generating storms there today. Yet, not every danger arrives on such enormous scale. Smaller atmospheric phenomena emerge frequently across these waters as well. Waterspouts, Narrow rotating columns extending between sea and cloud appear when unstable air interacts with rapidly changing surface conditions. Some remain delicate and short-lived, pale funnels wandering briefly across open water before dissolving back into rain. Others intensify into violent rotating towers capable of overturning small vessels or tearing apart exposed structures at sea. They can form with very little warning, especially where warm currents feed rapidly rising air beneath unstable storm systems. For ships crossing the Devil's Sea, these weather patterns create a dangerous lack of refuge. The corridor stretches far from major ports, and the surrounding islands provide limited shelter against rapidly intensifying storms. A vessel caught inside a strengthening typhoon cannot simply turn toward nearby safety. Distance itself becomes part of the hazard as crews navigate through immense moving systems generated by the restless heat of the Pacific Ocean below them. If the waters of the Devil's Sea could suddenly become transparent, the view beneath them would not resemble an empty plain, stretching quietly across the Pacific floor. The landscape below is fractured, mountainous, and immense, shaped by millions of years of tectonic pressure and volcanic upheaval. Entire mountain ranges rise unseen through darkness. Trenches descend into depths where sunlight has never reached. Vast abyssal plains spread between them like submerged deserts, silent beneath kilometers of moving water. Along the eastern boundary of the corridor lies the Ogasawara Trench, one of the deepest features in the western Pacific. Its floor reaches nearly 9,800 meters beneath the surface, approaching the depths of the Mariana Trench farther south. At such distances below sea level, the ocean ceases to resemble the familiar world of waves and weather above. Pressure builds relentlessly with depth until it exceeds more than 1,000 times the atmospheric pressure experienced at the surface. Human bodies cannot survive exposure there. Most ordinary machines cannot survive either. Metal bends, seals rupture, hollow spaces collapse inward under the weight of the ocean, pressing from every direction at once. Only a handful of specialized submersibles have ever descended into environments like these, and even those vehicles move cautiously through the dark, protected by thick pressure spheres engineered to resist forces almost impossible to imagine directly. Outside their reinforced walls, the water possesses a crushing density unlike anything present in the shallow seas of the continental shelf. The Devil's Sea conceals entire geological structures beneath conditions that naturally resist human exploration. The seafloor itself rises and falls continuously across the corridor. Seamounts emerge from abyssal depths like submerged volcanic islands that never quite reached daylight. Some climb thousands of meters upward before stopping only a few hundred meters below the surface. Hidden hazards capable of altering currents and wave behavior far above them. Between these underwater mountains lie steep valleys, trenches, ridges, and fractured volcanic plateaus formed through countless eruptions and tectonic collisions over geological time. This dramatic topography shapes the movement of the ocean in ways invisible from above. Deep currents flowing through the region encounter cliffs, slopes, and submerged peaks, forcing water into complex circulation patterns that interact across multiple layers of the Pacific. Cold, dense water slides beneath warmer layers. Currents wrap around seamounts in rotating spirals. Narrow passages accelerate flow like underwater wind tunnels moving through stone. Within these layered waters, internal waves travel silently through the ocean itself. Unlike ordinary surface waves shaped by wind, internal waves form along the boundaries, separating water masses of different density and temperature. Some rise hundreds of meters tall beneath the surface while leaving little visible trace above. Entire underwater ridges can trigger them as tidal flow moves across the sea floor, sending immense, slow-moving pulses through the ocean interior. Though hidden from direct sight, these internal waves influence the surface world indirectly. They alter current directions, disturb nutrient flow, and create shifting patterns of turbulence difficult for navigators to predict. A vessel crossing apparently calm water may unknowingly pass above enormous underwater movement, unfolding far below the hull. In regions as geologically active as the Devil's Sea, those interactions become even more complicated as earthquakes, volcanic heat, and changing topography continuously reshape the pathways through which deep water moves. Despite advances in sonar mapping and satellite observation, large portions of this underwater terrain remain only partially understood. The ocean floor here is too vast and too irregular for complete exploration using present technology. Even in recent years, researchers studying the broader Western Pacific have identified previously unknown seamounts through satellite altimetry, a method capable of detecting subtle bulges in sea surface height caused by the gravitational pull of underwater mountains hidden far below. The sea itself reveals these buried structures indirectly, bending water around them in ways detectable only through careful measurement from orbiting instruments. Somewhere beneath the Devil's Sea, there are almost certainly trenches, ridges, and volcanic formations that no human has yet mapped in detail. Landscapes existing in permanent darkness beneath one of the deepest and most restless regions of the Pacific Ocean. At the greatest depths beneath the Devil's Sea, where pressure crushes with the weight of entire oceans and sunlight has never once arrived, life continues in forms almost detached from the surface world above. The darkness there is not the darkness of night. It is older and more complete, a permanent absence stretching across trenches, volcanic ridges, and fractured plains hidden beneath kilometers of Pacific water. Yet within that unseen environment, entire ecosystems endure around sources of heat rising from the restless crust below. Along cracks in the seafloor, hydrothermal vents release mineral-rich water heated deep within the earth. The fluid emerging from these fissures can exceed temperatures of 120 degrees Celsius, yet under immense pressure, it does not boil. Instead, it pours upward into the freezing ocean like black smoke drifting through darkness. Around these vents, life gathers densely against the surrounding emptiness, forming biological communities powered not by sunlight, but by chemistry itself. On the surface of Earth, nearly all ecosystems ultimately depend upon the Sunday plants capture light. Animals feed upon those plants or upon each other in long chains tied back to photosynthesis. In the deep Pacific beneath the Devil's Sea, another process takes over. Chemosynthetic bacteria extract energy directly from chemicals rising out of the vents, particularly sulfides and methane released through volcanic activity. These microorganisms become the foundation of ecosystems existing entirely independent of sunlight, isolated from the surface in ways once thought impossible for complex life. Tube worms, several meters long, cluster around the vents in pale forests of soft living tissue, drawing nutrients from symbiotic bacteria living inside their bodies. Ghostly white crabs crawl across mineral chimneys coated in microbial mats. Tiny shrimp gather in dense swarms where superheated water meets the freezing sea. The environment shifts constantly as new vents open and old ones collapse beneath volcanic activity, yet life adapts continuously to the instability surrounding it. Some of the organisms inhabiting these depths appear almost unreal when illuminated by submersible lights for the first time. The Dumbo octopus, named for the ear-shaped fins extending from its body, has been observed at depths exceeding 7,000 meters within the western Pacific. It drifts slowly above the sea floor with delicate movements, one of the deepest living octopus species known to science. Unlike shallow water relatives hunting coral reefs or coastal shallows, it spends its entire existence in darkness, beneath crushing pressure where few predators or competitors can survive. Higher in the water column, between the abyss below and the distant surface above, another hidden world unfolds through living light. Bioluminescent organisms dominate many of the mid-depth layers within the Devil's Sea corridor. Fish, jellyfish, squid, siphonophores, and drifting plankton generate flashes, pulses, and glowing patterns through chemical reactions inside their own bodies. Some use light to lure prey. Others communicate, camouflage themselves, or confuse approaching predators. In these waters, the density and diversity of bioluminescent species appear especially rich, sustained partly by nutrients rising upward from volcanic and tectonic activity below. Among them moves the barrel-eye fish, one of the strangest vertebrates recorded in the Pacific. Its transparent head reveals rotating tubular eyes capable of turning upward through the darkness, searching for silhouettes, drifting faintly against the distant glow of surface light far above. For most of human history, creatures like this remained entirely unknown, existing unseen beneath shipping routes, crossed for centuries by sailors unaware of the biological world below them. Even now, the catalog of life in the region remains incomplete. Japanese researchers exploring the adjacent Ogasawara waters with deep-sea submersibles have recovered organisms that science has not yet formally classified. Some exist only as preserved samples awaiting careful analysis in laboratories. Others have been observed briefly on camera before disappearing again into darkness beyond the reach of collection equipment. The instability of the Devil's Sea may itself encourage biological diversity. Lava flows, collapsing sediment, and shifting volcanic terrain can isolate populations within separated pockets of the seafloor for long periods of time. Over generations, species adapt independently to those isolated environments, slowly diverging into new forms shaped by pressure, chemistry, and darkness beneath the Pacific Ocean. Old maritime records rarely read like modern investigations. Ink fades, dates blur across copied manuscripts. Storms are described through seasonal language rather than meteorological detail, and disappearances are often reduced to a single quiet line noting that a vessel failed to return. Yet within the long history of Japanese seafaring, the waters southeast of the mainland appear again and again in records marked by unusual loss. By the 12th century, references already existed describing ships vanishing within the same broad corridor later associated with the Devil's Sea, though the surviving documents remain too sparse to separate ordinary storms from stranger events unfolding beyond witness. As Japan's maritime administration modernized through later centuries, the records became more precise. Naval logs, fishing registries, and commercial shipping reports preserved increasingly detailed accounts of missing vessels, weather conditions, departure times, and intended routes. By the 20th century, the patterns surrounding the Devil's Sea had become difficult for authorities to dismiss as mere coincidence. Between the early 1950s and the middle of that decade, Japanese officials documented the disappearance of at least 9 vessels within the corridor, under circumstances not fully explained by known weather conditions alone. These were not isolated wooden fishing craft vanishing quietly during seasonal storms. Several were substantial commercial ships or research vessels, operating with trained crews and modern equipment for the era. Some disappeared so abruptly that no distress transmission reached coastal stations. Others left behind little or no recoverable debris, despite extensive search efforts across the surrounding Pacific. Investigators attempting to reconstruct events encountered the same recurring absence noted throughout earlier centuries. The ocean surface often offered almost nothing back. The Japanese government treated the situation with unusual seriousness. During the fragile years following the Second World War, maritime trade remained essential to economic recovery. Fuel, machinery, food supplies, and industrial materials all moved across Pacific shipping routes, connecting the rebuilding nation to the wider world. Rerouting vessels carried financial consequences Japan could scarcely afford during those years of reconstruction. Yet authorities formally designated portions of the corridor as dangerous waters, issuing warnings and diverting shipping traffic away from sections associated with repeated losses. That response alone separates the Devil's Sea from many other ocean legends. Maritime insurers and regulatory agencies rarely alter commercial routes without measurable concern supported by accumulated evidence. The decision reflected not folklore but institutional caution emerging from repeated incidents investigated by a seafaring nation with centuries of navigational experience behind it. Across the Atlantic, the Bermuda Triangle followed a very different trajectory. Its fame expanded primarily through magazines, television, and best-selling paranormal literature rather than through official maritime policy. Lloyd's of London, one of the world's largest maritime insurers, has never classified the Bermuda Triangle as an unusually hazardous shipping zone. Premiums for vessels transiting those waters remain consistent with ordinary maritime risk assessments. The United States Coast Guard has repeatedly stated that the number of disappearances associated with the region does not exceed statistical expectations for such a heavily traveled area of ocean. The Devil's Sea never became embedded within Western popular culture to the same extent, largely because relatively few Western ships crossed the corridor regularly, and because the historical documentation remained concentrated within Japanese sources, inaccessible to most English-language audiences. Yet among maritime historians and oceanographers familiar with the record, the Western Pacific Corridor has often been treated with greater scientific seriousness precisely because many of its hazards possess identifiable geological and oceanographic foundations. Even Charles Berlitz, whose writings helped transform the Bermuda Triangle into an international obsession, later acknowledged the Devil's Sea in a follow-up work published during the late 1980s, describing it as the Pacific counterpart to the Atlantic mystery. By then, however, researchers increasingly viewed the comparison differently. The Devil's Sea appeared not as a supernatural puzzle detached from science, but as a convergence zone where tectonic instability, submarine volcanism, extreme weather, navigational anomalies, and deep ocean geography intersected within the same corridor. The historical record does not present a single mystery with one hidden answer. Instead, it reveals centuries of encounters between human navigation and one of the most geologically restless stretches of ocean on Earth. Some mysteries become global legends not because they are the most dangerous, but because they arrive at the right moment in culture, language, and media. The Bermuda Triangle entered public imagination through a chain of storytelling events unfolding largely inside the United States during the middle of the 20th century. Before then, the region existed simply as another heavily traveled section of the Atlantic Ocean, crossed daily by military aircraft, cargo ships, fishing vessels, and private boats moving between Florida, Bermuda, and Puerto Rico. In 1964, A writer named Vincent Gaddis published an article in Argosy magazine that gathered several disappearances into a single narrative framework. He introduced the phrase Bermuda Triangle, transforming scattered maritime incidents into a connected mystery with a memorable name. The article arrived during a period when popular magazines increasingly blended journalism with speculative storytelling, particularly around unexplained phenomena, lost civilizations, and strange events occurring beyond ordinary understanding. The idea expanded dramatically a decade later through the work of Charles Berlitz. His book on the Bermuda Triangle, published in the 1970s, became an international sensation. More than 20 million copies circulated worldwide, translated into dozens of languages, and distributed across bookstores, television discussions, and documentary specials. The timing proved almost perfect. Public fascination with paranormal subjects had reached an unusual cultural peak. Interest in unidentified flying objects, psychic phenomena, ancient mysteries, and hidden worlds moved steadily through Western entertainment during those years, and the Bermuda Triangle fit naturally into that atmosphere of speculation. The Devil's Sea never experienced a similar cultural transformation. No best-selling English-language author devoted an entire global publishing campaign to the waters southeast of Japan. Most documentation surrounding the region remained buried inside Japanese maritime archives, scientific reports, government investigations, and local historical records unavailable to the wider English-speaking audience. The difference was not necessarily the strength of the evidence, it was access. Stories become global myths only when they cross linguistic and cultural borders large enough to reach mass audiences. Geography shaped the imbalance as much as language did. The Bermuda Triangle sits close to major American population centers and recreational boating routes. Florida alone provided millions of people living within direct proximity to the legend. Commercial flights crossed the region constantly. Cruise ships moved through nearby waters daily. American television networks, publishers, and news organizations operated close enough to treat the area as part of their immediate cultural landscape. The Devil's Sea existed far from those centers of influence. Positioned deep within the Western Pacific, the corridor lay beyond the ordinary routes of most Western travelers and commercial vessels. Few American or European ships crossed the region regularly, compared with the dense maritime traffic moving through the Atlantic near the Caribbean and eastern United States. For Western audiences, the Devil's Sea remained geographically distant, culturally unfamiliar, and linguistically obscured. In many ways, the contrast reveals how human attention operates. Societies often fear what is most visible to them rather than what is objectively most hazardous. A mystery discussed repeatedly through books, television, and newspapers begins to feel culturally significant regardless of the underlying evidence. Meanwhile, equally serious or even more credible phenomena can remain largely unknown when separated by geography, language, or limited media exposure. Researchers who have studied both regions frequently point toward an unusual irony hidden beneath the popular mythology. Most disappearances associated with the Bermuda Triangle can be explained through ordinary maritime factors. Sudden Atlantic storms, navigational mistakes, mechanical failures, and the sheer volume of traffic passing through the area account for the overwhelming majority of incidents. The region itself is not especially geologically unstable. Its magnetic behavior falls within normal navigational expectations. Its oceanography, while sometimes dangerous, is well studied and comparatively predictable. The Devil's Sea presents a different picture entirely. Beneath those Pacific waters lie active tectonic boundaries, submarine volcanoes, methane hydrate systems, magnetic irregularities, extreme depth, and rapidly intensifying weather patterns operating within the same corridor. Scientists do not treat the region as supernatural. They treat it as a place where multiple real hazards converge simultaneously, creating conditions still not fully understood even now. The ocean itself never chose which story the world would remember. Seen from orbit, the Pacific appears calm at first glance, a broad blue surface curving beneath cloud systems and sunlight. Yet within that immense expanse, entire rivers move through the ocean itself, carrying heat, nutrients, and momentum across thousands of kilometers without ever touching land. Along the eastern boundary of the Devil's Sea flows one of the largest of them all, the Kuroshio Current, second in strength only to the Antarctic circumpolar current surrounding the frozen southern continent. The scale of the Kuroshio is difficult to grasp through ordinary comparison. Every second, it transports roughly 50 million cubic meters of seawater northward through the western Pacific. By comparison, the Amazon River, the largest river on Earth by discharge, moves only a fraction of that amount into the Atlantic Ocean. The Kuroshio carries approximately 250 times more water than the Amazon, not through a visible channel bordered by land, but through open ocean guided by planetary rotation, wind patterns, and the shape of the Pacific Basin itself. The current begins in tropical waters warmed beneath equatorial sunlight before sweeping northward along the eastern coast of Taiwan and Japan. At the surface, its temperature can approach 28 degrees Celsius, significantly warmer than the surrounding Pacific waters through which it flows. Under certain conditions, the contrast creates a distinct deep blue coloration, visible even from satellites and high-altitude aircraft. This color inspired the current's name. In Japanese, Kuroshio means black stream, a description not of darkness, but of the rich indigo tone carried through the surrounding ocean. As the Kuroshio passes the Devil's Sea corridor, it encounters one of the most irregular submarine landscapes in the Pacific. Beneath the moving water rise volcanic ridges, submerged mountain chains, and seamounts extending upward from abyssal depths. The current does not flow smoothly across these structures. Instead, it bends, accelerates, and fractures into enormous rotating eddies that drift across the region like slowly turning atmospheric storms hidden within the ocean itself. Some of these eddies stretch across hundreds of kilometers. They trap warmer or colder water inside, rotating boundaries that persist for weeks or even months before dissolving back into the surrounding Pacific. Within them, conditions can shift unexpectedly across relatively short distances. Fog forms suddenly, where temperature gradients sharpen between water masses. Wave patterns change direction as rotating currents interact with wind and topography. Vessels entering such systems may experience altered drift speeds difficult to predict using ordinary navigation charts alone. For ships crossing the Devil's Sea, these rotating structures create subtle but important hazards. A vessel expecting steady movement along a planned route may instead encounter accelerated lateral drift, pulling it far from intended bearings over the course of several days. Before satellite navigation, such deviations accumulated quietly. Mariners steering by stars, currents, and magnetic compasses often discovered their estimated position no longer matched the surrounding sea or weather conditions. The Kuroshio also acts as a vast conveyor of atmospheric energy. Warm water releases heat continuously into the air above it, feeding evaporation and destabilizing surrounding pressure systems across the western Pacific. This transfer of heat becomes one of the major forces supporting typhoon development within the region. Storm systems passing above the current draw energy from water extending deep below the surface, allowing some tropical cyclones to intensify with unusual speed and persistence. For ancient sailors navigating wooden vessels through the Western Pacific, the Kuroshio existed as both opportunity and danger. A favorable crossing aligned with the current could shorten voyages dramatically, carrying ships northward with steady, invisible momentum beneath their hulls. Yet the same force could also push navigators far beyond familiar waters if weather, cloud cover, or navigational error interrupted their course. In open ocean with no visible landmarks, a strong current becomes difficult to detect directly. A vessel may appear to travel normally while drifting steadily into unfamiliar sections of the Pacific. The Kuroshio remains there still, moving through the Devil's Sea exactly as it has for thousands of years, a hidden river shaping weather, navigation, and the restless surface of the Western Pacific. For centuries, sailors told stories about waves that did not behave like ordinary seas. They described solitary walls of water rising suddenly from otherwise manageable conditions, towering far above surrounding swells before collapsing back into the ocean as though they had never existed. Maritime culture carried these accounts across generations, yet many scientists treated them with skepticism for most of the 20th century. Oceanographers assumed frightened crews had exaggerated storm conditions, misjudged wave heights, or merged several separate waves into distorted memory after surviving violent weather at sea. The mathematics of wave behavior appeared to support that skepticism. Statistical models suggested that truly enormous isolated waves should be exceptionally rare, almost impossible under ordinary ocean conditions. Then, during the winter of the mid-1990s, the sea produced an instrument reading impossible to ignore. On the first day of 1995, the Draupner oil platform in the North Sea recorded a wave rising approximately 25 meters above the surrounding ocean. Nearby waves averaged closer to 12 meters, already dangerous, but still within expected storm conditions for that region. The recorded wave towered far beyond those expectations. Steep and isolated, captured directly by instruments designed for industrial offshore operations. For the first time, modern science possessed undeniable evidence that rogue waves were real physical phenomena rather than maritime folklore. Satellite observations gathered during subsequent years revealed something even more unsettling. Rogue waves occurred far more frequently across the world's oceans than existing statistical models had predicted. Waves classified as rogue events are generally defined as waves exceeding twice the significant height of the surrounding sea state, towering abruptly above neighboring swells in ways that appear almost disproportionate to the wider ocean around them. Researchers still debate the exact mechanisms responsible for generating them consistently, though several contributing conditions have become increasingly clear. Rogue waves tend to emerge where separate wave systems intersect from different directions, compressing energy into unstable peaks. Strong currents flowing against incoming waves can steepen water rapidly, forcing wave energy upward rather than allowing it to spread naturally across the surface. Irregular seafloor topography also plays an important role by focusing wave energy into concentrated zones through underwater ridges, trenches, and submerged mountains. The Devil's Sea contains all of these conditions simultaneously. Typhoon-generated swells move across the Pacific, carrying enormous energy from distant storms. The Kuroshio Current flows through the region with tremendous momentum of its own, at times opposing wave direction depending on local circulation patterns and rotating eddies. Beneath the surface, volcanic ridges and seamount chains distort deep ocean movement, in ways researchers are still attempting to model fully. The result is a section of ocean where wave energy can interact chaotically across multiple layers of current, weather, and underwater geography. In deep ocean conditions, rogue waves can exceed 30 meters in height. Unlike long rolling swells rising gradually beneath a vessel, rogue waves often form steep faces with extraordinary force concentrated into a short horizontal distance. A large ship struck broadside by such a wave experiences stress far beyond the design assumptions of ordinary ocean travel. Hull structures twist violently, windows collapse inward, cargo shifts suddenly across decks. Even modern vessels can lose stability within moments under the impact of water carrying immense concentrated energy. Between the late 1960s and the middle 1990s, more than 200 supertankers and large commercial vessels were lost at sea worldwide. In many cases, weather reports alone could not fully explain the speed or severity of the sinkings. As understanding of rogue waves improved, oceanographers and maritime engineers began reconsidering several historical losses through a different lens. Some vessels may not have encountered impossible storms. They may have encountered singular waves emerging briefly from otherwise survivable seas. Within the Devil's Sea corridor, the probability of such events appears unusually elevated compared with calmer regions of the Pacific. The combination of unstable weather systems, intersecting wave trains, powerful currents, and fractured submarine terrain creates an environment where the ocean does not always follow the smoother statistical behavior once assumed by earlier generations of researchers. Even now, rogue waves remain difficult to predict precisely. They rise from ordinary water through converging energy, exist for moments, and disappear again into the surrounding sea, leaving behind only altered ships, fractured steel, or empty stretches of ocean continuing quietly beneath the sky. Imagine a cargo vessel crossing the Devil's Sea during the early 1950s, long before satellite navigation, digital weather forecasting, or continuous global communication networks existed. The ship moves through open Pacific water beneath a sky, thickening gradually with distant storm systems. Its crew relies upon compass bearings, radio schedules, paper charts, and dead reckoning calculations built from estimated speed and heading. Around them stretches only ocean, cloud, and the invisible forces operating beneath the hull. During typhoon season, sea conditions within the corridor could change rapidly across a single day. Swells arriving from distant storms intersected, with currents moving northward through the western Pacific, creating confused wave patterns difficult to navigate cleanly. Wind direction shifted unpredictably as pressure systems strengthened. Visibility narrowed beneath rain and low cloud. If the vessel's compass entered one of the magnetic irregularity zones scattered through the region, even a modest navigational deviation could quietly alter the ship's position over many hours, pushing it toward unstable sections of the corridor without the crew fully realizing the drift. Unlike modern navigators equipped with satellite positioning accurate to within meters, crews of that era depended heavily on approximation once coastlines disappeared from view. Celestial navigation became difficult beneath heavy weather. Radio direction finding offered only partial correction. Small errors accumulated silently across open water, especially inside a corridor already shaped by strong currents and irregular magnetic behavior. Now imagine that same vessel passing above an active volcanic region beneath the sea floor. Far below, geological pressure fractures sediment, layers containing trapped methane hydrates, while volcanic gas rises upward through submerged fissures. The ocean surface above may show little warning beyond unusual turbulence or patches of strangely disturbed water hidden among heavy seas. Beneath the hull, however, enormous volumes of gas begin expanding upward through the water column. As methane bubbles rise, the surrounding seawater loses density. Buoyancy weakens suddenly beneath the vessel. A ship designed carefully to float upon stable seawater encounters an environment no longer behaving according to ordinary marine physics. The hull begins dropping unevenly into aerated water incapable of supporting its weight properly. Engines strain against turbulence, while waves already generated by worsening weather strike from multiple directions. At the same moment, rogue wave conditions become possible. Intersecting swells, opposing currents, and unstable seafloor topography focus energy unexpectedly across the surface. A steep wall of water rises within already violent seas and strikes a vessel whose stability has already been compromised by reduced buoyancy below. The sequence unfolds too quickly for organized response. There is no orderly evacuation, no extended radio transmission explaining unfolding conditions. Steel fractures under combined stress while the sea closes over the ship in darkness and storm. This reconstruction aligns closely with the historical pattern investigators found most difficult to explain during the early disappearances. Ships vanished with little or no warning. Distress signals were absent or incomplete. Lifeboats rarely appeared. Search aircraft often found no spreading oil slicks or large debris fields, despite extensive operations across the corridor. The depth of the region offers part of the explanation. Much of the sea floor beneath the Devil's Sea descends between 6,000 and 9,000 meters into trenches and abyssal plains beyond the reach of mid-20th century recovery technology. A vessel sinking into those depths effectively disappeared from human access the moment it passed beneath the surface. Wreckage settled silently across dark sediment plains where no remotely operated vehicles yet existed to search. Any floating debris surviving the sinking faced another obstacle. The Kuroshio Current and surrounding Pacific circulation patterns carried material eastward into open ocean rapidly, dispersing fragments across vast distances far beyond the initial search zones Japanese authorities would logically prioritize. A scattered piece of wreckage drifting across the Pacific became almost impossible to trace back to its origin. Viewed together, the disappearances no longer require supernatural explanation. Earthquakes, submarine volcanism, methane release, rogue waves, magnetic anomalies, violent weather, immense depth, and powerful currents all existed within the same corridor simultaneously. Each force alone was dangerous. Combined, they created one of the least forgiving maritime environments on Earth. The ships did not vanish from reality. The Pacific simply absorbed them into a landscape too deep, too unstable, and too vast for recovery. Long before modern charts outlined the Pacific with precise coordinates and bathymetric lines, Japanese sailors were already recording the moods of the sea in careful detail. Japan's relationship with the ocean stretches back through centuries of fishing, trade, migration, warfare, and ritual, forming one of the longest continuous maritime traditions on Earth. Within that immense historical memory, the waters southeast of the mainland carried a particular reputation, quieter than myth at first, but persistent enough to survive across generations of written record and oral tradition. The name Ma-no Umi, often translated as the Sea of the Devil, appears in documents dating back to the Kamakura period between the late 12th and early 14th centuries. The phrase did not emerge from modern sensationalism or retrospective storytelling after 20th century disappearances. It existed long before industrial shipping, before sonar, before steam engines crossed the Pacific. Mariners navigating wooden vessels through those waters had already attached a distinct identity to the region, separating it from the surrounding ocean in both language and memory. Along the Izu Peninsula, fishing communities developed customs surrounding departures into the open Pacific. Small shrines overlooking harbors became places where offerings were left before voyages into uncertain water. Sailors prayed at particular times of year, often choosing departure windows according to seasonal rhythms passed down through families rather than formal meteorology. Certain stretches of the calendar were treated with unusual caution. Boats remained ashore longer during periods associated with unstable weather, rough currents, or strange behavior at sea. To modern eyes, these practices can appear purely spiritual, yet beneath the ritual existed generations of accumulated environmental observation. Communities without satellites or geological instruments still recognized recurring danger patterns through lived experience. The timing of ceremonies often aligned closely with typhoon seasons, unusual ocean conditions, or periods now understood to correlate with intensified volcanic and tectonic activity in the Western Pacific. Tradition became a way of preserving practical survival knowledge across centuries before scientific terminology existed to describe the forces involved. The Ogasawara Islands, isolated far out in the Pacific within the broader Devil's Sea corridor, reveal another layer of this relationship. Although formally annexed by Japan during the 19th century, fishermen and sailors had approached the surrounding waters cautiously for generations beforehand. Certain routes were preferred, while others gained reputations for unstable weather, difficult navigation, or disappearances difficult to explain through ordinary seamanship alone. In maritime cultures, dangerous places acquire memory slowly, built from repeated encounters rather than single dramatic events. The Pacific War deepened that memory further. During the 1940s, naval supply lines, submarine patrols, and military operations passed repeatedly through the same corridor, already weighted with centuries of maritime unease. Ships disappeared now not only to storms and currents, but to torpedoes, mines, aircraft, and underwater warfare. Yet within the collective imagination of post-war Japan, the boundaries between natural danger and wartime loss often blurred together. The same ocean that had taken fishing boats in earlier centuries now held military wreckage scattered across volcanic seafloor and abyssal depths. Post-war literature and folklore returned frequently to the image of the Devil's Sea as a place that takes things without returning them. The ocean became described not simply as hazardous, but as though it possessed intention or appetite. Ships entered and failed to emerge again. Objects vanished beneath the surface without trace. Families waited along coastlines with no bodies recovered and no graves to visit. Over time, language shifted subtly from describing danger to describing character. This tendency to anthropomorphize the sea reveals something deeply human rather than irrational. When communities face danger that behaves according to patterns they cannot fully control or explain, the mind often begins assigning personality to the force itself. Storms become temperamental. Oceans become watchful. Dangerous places acquire reputations almost like living presences. In the Devil's Sea, centuries of unpredictable loss shaped an emotional geography alongside the physical one, embedding caution into ritual, memory, and story long before science began uncovering the geological systems operating beneath the waves. Even now, traces of that older relationship remain, carried quietly through coastal traditions beside the restless Pacific. Most islands feel permanent when viewed from shore. Forests settle across them, birds nest within them, and generations of people begin treating them as fixed pieces of the world. Yet inside the Devil's Sea, the boundary between ocean and land is far less stable than it appears. Beneath the surface, volcanic forces continue reshaping the Pacific floor in real time, lifting mountains upward through darkness until they breach the sea itself, while elsewhere, entire formations collapse back beneath the waves almost as quickly as they emerged. This process has unfolded repeatedly within recorded human history. The Devil's Sea is not only a corridor of storms and currents, but also a region where the Earth continues building geography before human eyes. Submarine volcanoes rise from abyssal depths, carrying molten rock upward through fractures in the crust. Over years, centuries, or sometimes sudden eruptions, these volcanic structures accumulate layer upon layer of cooled basalt until the summit finally reaches the surface. An island appears where open ocean existed before. Some survive, others vanish again beneath erosion, collapse, or renewed volcanic violence. Within the Ogasawara island chain lies Nishinoshima, one of the clearest modern examples of this restless geological process. During the early 21st century, eruptions dramatically reshaped the island over remarkably short timescales. Between the years 2013 and 2014, volcanic activity expanded Nishinoshima substantially, adding approximately 2.7 square kilometers of entirely new land. Lava flowed directly into the surrounding Pacific, where it cooled into black volcanic rock, extending the island outward against the sea. Satellite imagery captured the transformation almost continuously. Shorelines shifted month by month. New ridges formed where only open water had existed previously. Ash plumes drifted upward into the atmosphere, while incandescent lava crossed fresh terrain, still steaming from contact with seawater. For geologists, the island became something extraordinary, a living laboratory where the same processes responsible for building continents across billions of years unfolded within the span of a single human observation cycle. The activity did not end there. During the years 2019 and 2020, further eruptions reshaped Nishinoshima again. Lava extended the coastline even farther, while simultaneously destroying much of the vegetation that had begun reclaiming the earlier volcanic surfaces. Life established itself cautiously across cooling rock, only to be erased again beneath renewed geological activity. The island existed in a continual state of becoming rather than permanence. What makes the Devil's Sea particularly unusual is that many eruptions never fully breach the surface at all. Vast volcanic events can unfold entirely underwater while still altering the surrounding ocean dramatically. A submarine eruption may create new ridges, collapse sections of seafloor, or release immense volumes of heated gas and ash into the water column without producing a visible island above the surface. Yet, even unseen, these eruptions reshape navigation corridors and local sea conditions in profound ways. Some Japanese researchers studying historical disappearances have proposed that certain unexplained losses may correspond to precisely these kinds of submarine volcanic events. A vessel passing through the corridor during an underwater eruption could encounter violent, localized disturbances impossible to predict using ordinary weather observation alone. Superheated water, ash, toxic gases, turbulence, and rapidly changing buoyancy conditions might combine into what was effectively a volcanic storm occurring at sea level itself. To sailors witnessing such phenomena, without geological context, the ocean would appear to transform unpredictably around them. Water could boil with trapped gases. Ash clouds might emerge suddenly from otherwise empty sea, surface conditions could deteriorate within minutes despite no visible coastline or terrestrial volcano nearby. In a region already shaped by unstable weather and difficult navigation, these eruptions added another layer of unpredictability beneath the surface. Perhaps the most disorienting aspect of the Devil's Sea is not simply that it contains danger, but that the geography itself remains unfinished. Mountains continue rising through the Pacific floor. Islands grow, fracture, and change shape across periods short enough for human beings to witness directly. The boundary between land and ocean behaves less like a fixed border and more like an ongoing negotiation between fire and water, continuing quietly beneath the waves. For most of human history, the deepest parts of the Devil's Sea remained unreachable, not only physically, but conceptually. Sailors crossed above those waters without any ability to see the terrain below them. Early sonar revealed only rough outlines. The abyss itself remained hidden beneath kilometers of pressure and darkness that no diver could survive. It was not until the late 20th century that technology finally became capable of descending into the depths where the region's geological forces actually operated. Japan became the leading nation in that exploration through the work of the Japan Agency for Marine Earth Science and Technology, widely known as JAMSTEC. Using specialized research vessels and deep-sea submersibles engineered for extreme pressure environments, researchers gradually began mapping sections of the Devil's Sea floor directly, rather than inferring its structure indirectly from surface measurements. Among the most important of these vehicles was the Shinkai 6500, a crude submersible capable of descending approximately 6,500 meters into the Pacific abyss. Each descent carried scientists into an environment more alien than almost any landscape on the surface of Earth. Sunlight vanished completely long before the vehicle approached the sea floor. Outside the viewing ports stretched black water under pressures strong enough to collapse ordinary metal structures instantly. Yet within that darkness, the submersibles found evidence confirming that the Devil's Sea was not merely a dangerous navigation corridor at the surface. The entire geological foundation beneath it remained intensely active. Researchers documented hydrothermal vent systems releasing mineral-rich, superheated water directly from fractures in the crust. Fresh lava flows appeared across sections of the seafloor where volcanic activity had occurred relatively recently on geological timescales. Sediment layers showed signs of disturbance consistent with underwater earthquakes, landslides, and eruptive events still reshaping the terrain beneath the Pacific. Perhaps most surprising were the discoveries that did not match existing charts at all. New seamounts emerged from survey data, where previous maps showed only open deep water. Some rose thousands of meters upward from abyssal plains, while remaining hidden below the surface by only a few hundred meters. Two vessels navigating overhead without accurate bathymetric information, such structures represented major hazards capable of altering currents and sea conditions invisibly. A seamount rising to within 200 meters of the surface may never break through the water visibly, yet it changes the ocean above it profoundly. Currents accelerate and bend around the submerged mountain. Wave patterns become irregular as deep water movement interacts with rising terrain. Internal waves form beneath the surface, while eddies rotate across surrounding waters. A ship crossing above such a feature without chart awareness may encounter sea behavior entirely different from the wider Pacific around it. During expeditions in the early 21st century, JAMSTEC researchers documented hydrothermal vent fields within the Devil's Sea corridor, producing water temperatures exceeding 300 degrees Celsius. Under ordinary atmospheric conditions, water at such temperatures would instantly become steam. Yet at extreme depth, immense pressure prevents boiling, allowing superheated liquid to pour continuously from volcanic fissures into freezing surrounding seawater. Around these vents, scientists found living ecosystems unlike anything previously imagined in traditional biology. Microorganisms thrived within chemically hostile conditions, once assumed incompatible with life. These extremophiles did not depend on sunlight or photosynthesis. Instead, they metabolized hydrogen, hydrogen sulfide, and other chemicals emerging from volcanic activity itself, converting geological energy directly into biological survival. This discovery carried implications extending far beyond the Devil's Sea. It suggested that life does not necessarily require sunlight at all, only a stable energy source and suitable chemistry. Entire ecosystems could exist independently from the surface world, powered by the internal heat of the planet rather than by the sun above. The deeper researchers explored the corridor, the more the Devil's Sea transformed from a maritime mystery into something scientifically richer and more complex. The region revealed itself not merely as hazardous water crossed by ships, but as a living intersection of tectonics, chemistry, biology, and ocean physics operating simultaneously across immense depth. Even now, only fragments of that abyss have been observed directly. Beyond the illuminated beams of each descending submersible, the Pacific floor continues outward into darkness, still largely unseen by human eyes. Modern maritime science approaches ship disappearances very differently from the way investigators approached them during the middle of the 20th century. Researchers no longer search for singular mysterious causes hidden behind isolated events. Instead, they study convergence, the alignment of multiple dangerous conditions within a narrow span of time where human response becomes impossible. In deep ocean disasters, catastrophe often emerges not from one overwhelming force alone, but from several smaller forces interacting faster than a crew can recognize what is happening around them. Within the Devil's Sea, this understanding has changed the way historical losses are interpreted. The region contains an unusually dense overlap of geological instability, volatile weather systems, extreme depth, strong currents, magnetic irregularities, and submarine volcanic activity. Each factor can threaten navigation independently. Combined, they create sequences of failure capable of overwhelming even experienced crews. One scientifically plausible scenario begins far beneath the surface. A vessel crosses above a section of sea floor, destabilized by volcanic activity or tectonic disturbance. Methane hydrates trapped under pressure fracture suddenly, releasing enormous gas volumes upward through the water column. At the surface, the sea may appear only slightly disturbed at first, hidden beneath ordinary storm conditions. Yet the physical properties of the water below the ship change rapidly as bubbles reduce density. The vessel loses buoyancy almost instantly. Instead of floating upon stable seawater, the hull begins sinking into aerated water, incapable of supporting its weight. In calm conditions, a crew might still have seconds to react, but inside the Devil's Sea, such events rarely occur in isolation. Heavy weather, unstable waves, and violent surface motion already strain the vessel. Once buoyancy collapses, recovery becomes impossible. Maritime simulations suggest the transition from stable navigation to complete loss could occur in under a minute, far too quickly for coordinated distress, communication, or evacuation. Another scenario unfolds more gradually, yet ends the same way. A ship navigates through a magnetic anomaly zone while weather deteriorates across the corridor. Compass bearings shift subtly from true direction. Before satellite navigation existed, even small deviations accumulated dangerously across open Pacific water. The vessel drifts incrementally off course while the crew continues believing their position remains accurate according to dead reckoning calculations. Hours later, the ship enters an area where strong current convergence interacts with typhoon-driven seas. Swells strike from conflicting directions, while rotating eddies alter vessel handling unpredictably. Under those conditions, one catastrophic wave impact becomes increasingly likely. A rogue wave or severe beam strike arrives against a ship already compromised by navigational disorientation and extreme sea state. To investigators afterward, the disappearance appears sudden, yet, from the perspective of physical systems, the catastrophe began hours earlier through invisible accumulated drift. There exists a third possibility less familiar to public imagination, yet equally dangerous. Deep beneath the Devil's Sea, nearby subduction boundaries remain under constant tectonic stress. An underwater earthquake does not always generate the towering coastal tsunamis associated with television footage and shoreline destruction. In deep ocean, tsunami energy often travels as a broad pulse wave, moving with extraordinary speed beneath the surface. A vessel crossing above a seamount or confined underwater valley during such an event may experience abrupt vertical displacement as sea level rises rapidly beneath it. Researchers estimate that localized deep ocean tsunami pulses can elevate surrounding water by 10 to 30 meters within moments, depending on sea floor geometry and energy focusing. In rough weather or unstable conditions, such displacement may destabilize a vessel before the crew fully comprehends what has occurred. Across all these models, the final pattern remains remarkably consistent. Distress signals fail to transmit completely, debris fields remain sparse or scattered, survivors rarely emerge. Not because anything supernatural intervened, but because the physical forces involved operate across scales and speeds that exceed ordinary human reaction time. The Devil's Sea stands apart because few places on Earth contain all these mechanisms simultaneously within the same corridor. Geological violence, unstable currents, magnetic disruption, rogue wave conditions, methane release zones, and deep ocean seismic activity overlap there continuously, transforming the region into a place where multiple independent hazards can converge without warning beneath an otherwise ordinary horizon. Far beneath the Devil's Sea, the floor of the Pacific is never truly still. Massive tectonic plates press against one another continuously in darkness, hidden below kilometers of water and rock. Along the subduction boundaries, beneath this corridor, one plate is forced slowly downward beneath another, descending into the Earth's mantle over spans of geological time almost impossible for human intuition to grasp. Yet the motion is not smooth. Pressure accumulates gradually where the plates lock together, storing energy silently across decades or centuries until the boundary finally slips. When that release occurs, the ocean above responds almost instantly. A tsunami begins not as a towering wall of water, but as a sudden displacement of the sea itself. The seafloor shifts upward or downward during an earthquake, lifting or dropping the entire water column above it. That displaced water then radiates outward across the ocean in every direction, carrying enormous energy through the Pacific Basin at extraordinary speed. The nearby subduction system connected to the Devil's Sea produced one of the most devastating examples in modern history during the early 21st century. The Tohoku earthquake and tsunami, generated along this broader tectonic boundary, sent waves crashing into the Japanese coastline, with heights reaching more than 40 meters in some areas, the highest tsunami run-up ever recorded in Japan. Entire coastal towns disappeared beneath the water within minutes, while the energy from the earthquake traveled outward across the Pacific Ocean itself. Yet in deep ocean, a tsunami rarely resembles the dramatic breaking wave most people imagine. Far from shore, the passing energy often appears only as a broad and rapid rise in sea level, sometimes little more than 1 or 2 meters in height. The danger comes not from visible steepness, but from scale and speed. Tsunami energy can travel through deep water at velocities approaching 900 kilometers per hour, crossing entire ocean basins with astonishing momentum. A ship floating in very deep water during such an event may experience surprisingly little direct disturbance. The vessel rises and falls gradually with the passing water mass, often without crews fully recognizing a tsunami has moved beneath them at all. But conditions change dramatically when tsunami energy interacts with irregular underwater terrain. The Devil's Sea contains precisely the kind of submarine geography capable of amplifying these forces. Seamounts rise abruptly from abyssal depths toward much shallower water. Trenches, ridges, and confined underwater valleys interrupt the smooth movement of ocean energy across the corridor. When tsunami waves encounter these structures, the energy compresses and intensifies. Water forced upward over rising terrain gains height rapidly, while narrowing valleys can funnel and focus the moving wave into concentrated zones of extreme turbulence. A vessel positioned above a shallow seamount, surrounded by very deep water, may therefore encounter conditions radically different from the surrounding Pacific. Sea level can rise abruptly beneath the hull, while wave patterns distort unpredictably as energy reflects and converges around underwater structures invisible from the surface. In heavy weather or unstable seas, such sudden displacement becomes especially dangerous. Japanese tsunami researchers have studied the Devil's Sea extensively because its complex seafloor provides a natural laboratory for understanding how underwater geography alters tsunami behavior before waves reach coastlines. Computer simulations and bathymetric mapping reveal that even relatively modest tsunami pulses can behave unpredictably once interacting with fractured volcanic terrain beneath the corridor. Earthquakes are not the only trigger. The steep slopes surrounding submarine volcanoes and seamounts remain vulnerable to underwater landslides when seismic shaking destabilizes accumulated sediment. Entire sections of seafloor can collapse downslope suddenly, displacing water locally and generating compact tsunamis independent of major surface earthquakes. These events may affect only limited regions of ocean, yet still create violent conditions for vessels nearby. Inside the Devil's Sea, this means dangerous sea level disturbances can emerge with little warning, even when no visible coastal tsunami exists elsewhere across the Pacific. The geological machinery beneath the corridor remains capable of reshaping the ocean's surface at any moment, transferring energy upward from the deep earth into the moving water above through processes as ancient as the planet itself. Far above the fractures and volcanic ridges beneath the Devil's Sea, the atmosphere appears at first detached from the geological violence below. Clouds gather, winds shift, pressure rises and falls, all with the familiar rhythms of weather systems moving across the Pacific. Yet in this corridor, the boundary between ocean and atmosphere becomes unusually intimate. Heat rising from the deep earth enters the sea itself, and from there, slowly, invisibly, begins shaping the sky. The ocean floor beneath this region contains dense networks of hydrothermal vents and active submarine volcanic systems. Through cracks in the crust, superheated water escapes continuously into the surrounding sea, carrying dissolved minerals and geothermal energy upward from below the tectonic plates. During periods of increased volcanic activity, these systems release enough heat to alter local water temperatures measurably, particularly around shallower submarine structures where rising thermal plumes approach the surface more efficiently. In most regions of the world, ocean, sea surface temperature depends primarily on sunlight, seasonal variation, and the movement of currents. Inside the Devil's Sea, another source contributes quietly from below. The sea itself is heated not only from above by the sun, but from beneath by geological processes unfolding in darkness. That detail matters enormously because warm surface water is the primary fuel source for tropical cyclones. Typhoons draw their strength from heat stored within the upper layers of the ocean. As warm water evaporates, moist air rises into the atmosphere and releases latent heat while condensing into clouds. That released energy feeds the storm system continuously, allowing winds to intensify and pressure to fall further. The Kuroshio Current already transports immense quantities of tropical warmth northward through the corridor, maintaining surface temperatures significantly higher than surrounding Pacific waters. But where that current passes above volcanically active zones, additional geothermal heating may create localized pockets of unusually warm water embedded within the broader flow. These become invisible reservoirs of extra atmospheric energy. Meteorologists studying Pacific storm behavior have observed that typhoons passing across certain sections of the Devil's Sea sometimes intensify faster than surrounding ocean conditions alone would predict. In some cases, storms strengthen abruptly within relatively short periods, drawing unexpected energy from the sea beneath them. Areas above submarine volcanic activity are increasingly studied as potential intensification hotspots, regions where additional heat entering the water column may subtly influence storm development overhead. The relationship becomes even more complex once the atmosphere responds. As typhoons strengthen, their rotating winds churn the ocean violently. Surface layers mix downward while deeper water rises upward through turbulent motion. Around seamounts and volcanic ridges, this vertical mixing interacts with already unstable thermal conditions below. Storm systems may therefore alter how heat disperses upward from hydrothermal zones, redistributing energy across the corridor in patterns. Researchers are still attempting to model accurately. In this way, the sea floor and atmosphere participate in a continuous exchange. Geological heat influences the ocean surface. The ocean surface fuels storms. The storms reshape the ocean itself. Unlike coastlines, covered in dense networks of weather stations and satellite-monitored infrastructure, much of the Devil's Sea remains comparatively isolated. Vast sections of the corridor contain active submarine systems that cannot be monitored continuously in real time. Many volcanic structures remain only partially mapped, and fluctuations in geothermal output may occur far below the reach of direct observation. This creates a lingering uncertainty in forecasting conditions across the region. Meteorologists can track currents, pressure systems, and storm formation with extraordinary sophistication, yet one variable remains unusually difficult to measure consistently: the restless geology beneath the water itself. Elsewhere in the Pacific, the ocean floor behaves mostly as stable terrain underlying atmospheric processes. Here, the crust participates actively in the weather above. The boundary between Earth and ocean softens into something more interconnected, a place where storms drifting through the night sky may carry faint traces of volcanic heat that began rising from the mantle far below the deepest water. Long before human instruments reached these waters, an immense migration was already unfolding beneath the Pacific each night. As darkness spread across the surface, entire layers of living creatures began rising slowly upward from the depths, ascending through cold black water toward the faint remains of evening filtering down from above. By dawn, they would descend again, retreating beneath the reach of sunlight into a hidden realm suspended between surface and abyss. Oceanographers call this region the Mesopelagic Zone, though sailors once knew it only as a place where the sea occasionally glowed beneath their hulls. It stretches from roughly 200 to 1,000 meters below the surface and is often called the Twilight Zone because light still exists there, but only barely. The sun survives as a dim blue haze, too weak for vision over distance, too faint to sustain ordinary surface life. In the Devil's Sea, this middle layer is unusually rich. Nutrients rise continuously from below through volcanic upwellings, while the Kuroshio Current folds warm and cold water masses together in restless motion. The result is a corridor where microscopic life flourishes in extraordinary density, feeding vast populations of drifting and swimming organisms hidden far beneath the visible ocean. Every night, billions of animals begin moving upward through this zone in what scientists now recognize as the largest biomass migration on Earth. Tiny crustaceans, squid, gelatinous colonies, and fish rise toward surface waters under cover of darkness to feed, then descend again before daylight returns. The movement is so immense that early naval sonar operators sometimes mistook these living layers for the seafloor itself. Within the Devil's Sea corridor, much of this migration remains poorly documented. Lanternfish drift upward, carrying rows of bioluminescent organs glowing softly along their bodies like distant windows in darkness. Bristlemouth fish move among them in impossible numbers. Though individually small and rarely seen by humans, they may collectively represent the most numerous vertebrate animals on Earth. Far stranger shapes move more slowly through the water. Among the most remarkable are siphonophores, creatures that appear at first glance to be single, enormous animals but are in fact living colonies composed of specialized individuals called zooids. Each zooid performs one function only. Some pulse rhythmically for movement. Others capture prey with venomous tentacles. Others reproduce. Together they operate as a unified organism stretched through the water like drifting architecture made of translucent flesh. Certain siphonophores observed in Pacific deep waters extend to lengths approaching 40 meters, longer than a blue whale. Their bodies trail invisibly through darkness in delicate chains that can pulse with bioluminescent flashes when disturbed, creating brief rivers of blue light far below the surface world. The richness of this twilight ecosystem supports larger hunters as well. Sperm whales enter these waters regularly, descending through the Mesopelagic Zone and deeper still in search of squid concealed within total darkness. Their dives can last more than an hour, carrying them into pressure levels that would destroy unprotected human bodies instantly. Sight becomes nearly useless there. Sound replaces it. Sperm whales navigate and hunt through echolocation, producing focused clicking pulses of extraordinary intensity. Some clicks reach approximately 230 decibels, making them the loudest biological sounds produced by any known animal. Hydrophones lowered into the Devil's Sea have recorded these sounds echoing through deep water layers where sunlight has never penetrated, sharp metallic bursts traveling immense distances through the cold Pacific dark. Between the illuminated surface and the volcanic abyss below exists this immense suspended world, crowded with migrations, signals, predators, drifting colonies, and living lights. It is neither shallow ocean nor true deep sea, but an intermediate realm where creatures rise and vanish with the rhythm of darkness itself, hidden inside waters that from above appear calm, empty, and silent. Scattered across the western Pacific, far from the crowded coastlines of mainland Japan, the Ogasawara Islands rise from the ocean like fragments carried upward from another world. The sea surrounding them stretches immense and open in every direction, interrupted only by volcanic silhouettes and long swells moving beneath the trade winds. At first glance, the islands appear calm and almost detached from the geological violence surrounding them. Yet every ridge, cliff, and forested slope exists because of the same restless forces shaping the Devil's Sea below. The archipelago, also known as the Bonin Islands, lies directly within the corridor long associated with disappearances, volcanic instability, and shifting seas. Yet, unlike the dramatic reputation surrounding the wider region, the islands themselves are places of remarkable biological quietness. They are among the most ecologically unique island systems on Earth, precisely because they were never connected to any continent. These are true oceanic islands. No ancient land bridge ever joined them to Asia or any larger landmass. Every living organism that established itself there arrived across open ocean. Seeds drifted on currents. Birds crossed immense distances through storms and prevailing winds. Insects traveled unnoticed on floating vegetation. Life arrived slowly, one accidental journey at a time. Isolation transformed that life into something distinct. Without mainland predators or competitors, species evolved along unusual paths found nowhere else on Earth. Tiny land snails diversified into forms unique to individual islands. Certain plants adapted to volcanic soils and salt-heavy winds with no equivalent relatives elsewhere. Birds nested in ecosystems where the balance between species developed over immense stretches of uninterrupted time. Evolution proceeded there like a long private conversation between ocean, climate, and isolation. Scientists often compare the Ogasawara Islands to remote evolutionary laboratories, such as the Galapagos, though the atmosphere here feels different, quieter, and more secluded within the Pacific immensity. In recognition of this biological importance, the islands were designated a UNESCO World Heritage Site in the early 21st century for their extraordinary ecological value and their role in demonstrating how evolution unfolds in isolation. Yet beneath these forests and cliffs lies the same unstable foundation that defines the wider Devil's Sea. The islands themselves are volcanic in origin, the exposed summits of ancient submarine volcanoes rising upward from the Pacific floor over geological time. Long before humans crossed these waters, eruptions beneath the ocean slowly built mountains tall enough to break the surface. Lava cooled into rock, rain collected, seeds arrived. Forests formed atop structures born from tectonic collision and mantle heat. Even now, the surrounding seafloor remains active. Earthquakes ripple through the region regularly. Nearby submarine volcanoes continue reshaping underwater terrain beyond the visible horizon. The apparent serenity of the islands exists within a much larger environment still in motion beneath the sea. Human life persists there nonetheless. Approximately 2,400 people live permanently across the main inhabited islands, making them some of the most isolated residents anywhere under Japanese administration. Reaching the archipelago from Tokyo requires a ferry journey lasting roughly 24 hours across open Pacific water. No airport connects the islands to the mainland. Weather and sea conditions still dictate movement in ways largely forgotten by more connected parts of the modern world. For those who live there, the Devil's Sea is not primarily a legend or symbolic place. It is simply the surrounding environment, crossed routinely for fishing, transport, research, and daily life. The relationship is practical rather than mythological. Residents understand the sea's instability through experience, weather reports, seasonal rhythms, and inherited local knowledge rather than sensational stories. At night, when the ferry routes quiet and the Pacific darkens beyond the harbor lights, the islands remain suspended within one of Earth's most geologically active ocean corridors. Forests cling to volcanic stone above trenches thousands of meters deep. Waves move across water concealing hydrothermal vents, migrating life, submarine ridges, and shifting tectonic boundaries below. Yet amid all that movement, human communities continue living quietly upon the peaks of ancient underwater mountains rising through the Pacific dark. Long after storms have dissolved and volcanic eruptions have cooled beneath the Pacific, the sea floor continues, preserving another layer of memory in silence. Beneath the currents of the Devil's Sea rests scattered metal, fractured hulls, collapsed aircraft frames, and machinery once carried into war across open ocean. The geological violence shaping this corridor did not pause during the 20th century. Human conflict entered it instead, adding another history to waters already marked by centuries of disappearance and danger. During the Pacific War, the corridor surrounding the Devil's Sea became one of the major maritime pathways connecting the Japanese mainland to island territories spread across the western Pacific. Supply ships, troop transports, destroyers, submarines, and aircraft carriers moved repeatedly through these waters carrying fuel, weapons, food, and personnel toward distant island chains whose survival depended entirely on ocean routes remaining open. American naval strategy focused heavily on severing those routes. Submarine operations intensified across the Pacific as the war progressed, targeting Japanese shipping lanes with increasing effectiveness. The waters surrounding the Devil's Sea became part of a vast, submerged battlefield where vessels often vanished without witnesses, disappearing into storms, darkness, or sudden explosions far from land. Much of that wreckage still remains below. Unlike battlefields on land, where destruction can be mapped and revisited openly, the ocean conceals its history beneath depth, pressure, and moving sediment. Large portions of the seafloor inside this corridor remain only partially surveyed even today. Countless wrecks from wartime operations likely rest unexamined across trenches, volcanic slopes, and abyssal plains thousands of meters below the surface. Some vessels descended intact before collapsing gradually under pressure. Others shattered on impact against submarine ridges or volcanic terrain hidden beneath rough seas. Aircraft lost during naval engagements drifted downward through kilometers of water before settling into darkness, where corrosion proceeded slowly in the cold Pacific depths. Nearby waters also witnessed one of the largest naval aviation battles in human history. During the Battle of the Philippine Sea in the middle years of the war, enormous carrier fleets clashed across adjacent Pacific regions in an engagement so devastating to Japanese naval aviation that American pilots later gave it a grimly mocking nickname, describing the destruction of attacking aircraft with unsettling casualness born from wartime exhaustion. Yet, even amid advanced military operations involving radar, sonar, naval charts, and experienced navigators, the corridor continued resisting certainty. Submarine crews operating within these waters reported navigational difficulties that often resembled much older maritime accounts preserved in Japanese records centuries earlier. Compasses occasionally behaved unpredictably. Currents pushed vessels away from projected positions. Depth readings sometimes conflicted with available charts. Underwater terrain proved more complicated than expected, particularly around volcanic structures and steep submarine ridges. These were not inexperienced sailors, exaggerating unfamiliar seas. They were trained naval officers, operating sophisticated wartime vessels, equipped with some of the most advanced maritime technology available during the era. Their reports added a modern military layer to observations long embedded within regional maritime culture. Over time, the wreckage itself became part of the ocean ecosystem. Steel hulls resting in darkness slowly accumulated marine growth. Coral colonies established themselves along fractured decks and artillery mounts. Fish moved through broken passageways once filled with machinery and human voices. Invertebrates colonized surfaces exposed to nutrient-rich currents flowing across the sea floor. What began as instruments of war gradually transformed into artificial reefs, integrated into deep Pacific biology. At extreme depths, recovery becomes nearly impossible. Many wrecks lie far below the operational range of conventional salvage systems, pressed beneath water columns heavy enough to collapse most submersibles, not specifically designed for abyssal exploration. Sediment settles slowly across them year after year, while tectonic motion subtly reshapes the terrain around their resting places. The Devil's Sea, therefore, contains not only volcanic mountains, hydrothermal vents, and migrating deep ocean life, but also the remains of a human conflict layered quietly into the geology itself. Metal returns gradually to mineral form. Coral overtakes machinery. Navigation routes vanish beneath shifting currents. The ocean absorbs even war into its own immense continuity, carrying human history downward into darkness beside everything else it keeps. From orbit, the Pacific Ocean appears smooth and complete, its surface mapped continuously by satellites tracing weather systems, currents, and shifting clouds across the planet. Yet, beneath that reflective skin lies a geography humanity still knows only partially. The deeper regions of the Devil's Sea remain among those unfinished spaces, areas where mountains, trenches, and entire ecosystems continue existing beyond detailed human observation. Modern oceanography has advanced enormously during the past few decades. Research vessels now carry multi-beam sonar systems capable of generating detailed maps of the seafloor. Deep submersibles descend farther than earlier generations could survive. Satellites detect subtle variations in sea surface height caused by gravitational pull from underwater features below. Even so, large portions of Earth's ocean floor remain unresolved at high detail, known only through broad approximations rather than precise topographic understanding. To address that absence, an international effort known as the Seabed 2030 Project was established through collaboration between the General Bathymetric Chart of the Oceans and the Nippon Foundation. Its goal is ambitious and remarkably recent in human history: to produce a complete high-resolution map of the entire global ocean floor within the first half of the 21st century. The fact that such a project is still necessary reveals how incomplete humanity's knowledge of the deep ocean remains. As of the middle years of the present decade, only approximately 1/4 of the global seafloor has been mapped at truly high resolution. The remaining majority exists in scientific outline rather than detail, represented by coarse data that smooths away smaller ridges, valleys, volcanic structures, and geological complexity. Vast sections of abyssal terrain remain effectively unseen. The Devil's Sea contains several of these poorly resolved regions. Its trenches descend through extreme depths difficult to survey consistently. Strong currents complicate mapping operations. Volcanic activity reshapes terrain over geological and sometimes human timescales. Certain sections of the corridor remain visited only rarely by research expeditions because of distance, weather, and operational cost. Beneath those waters, the Pacific floor almost certainly contains submarine structures that have never appeared on detailed navigational charts. Some of those structures may be seamounts, rising thousands of meters upward from abyssal plains below. Unlike islands, they remain hidden beneath the surface entirely, invisible to ships crossing above them. Yet their presence alters currents, wave behavior, sediment flow, and biological distribution throughout the surrounding water column. An uncharted seamount is not merely a scientific curiosity. Maritime history contains multiple examples of vessels lost or damaged after encountering poorly charted underwater hazards. In the early years of the present century, the cargo vessel MV Rena grounded near New Zealand after striking a reef associated with charting inaccuracies rather than navigational recklessness. The event demonstrated how even in the satellite era, incomplete understanding of underwater geography can still produce catastrophe. Inside the Devil's Sea corridor, where weather, volcanic activity, and deep currents already complicate navigation, undiscovered submarine terrain carries even greater significance. The biological implications are equally profound. Every unmapped trench wall, volcanic ridge, and isolated abyssal valley may support ecosystems no human being has ever observed directly. Species adapted to pressure, chemistry, darkness, and thermal conditions unique to those environments continue living regardless of whether science has documented them. Some may resemble known deep ocean organisms. Others may occupy ecological niches, still absent from biological classification entirely. This is not metaphorical language about mystery or imagination. It is a literal statement about the present boundary of human knowledge. There are living creatures on the floor of the Devil's Sea that no person has ever seen. The ocean keeps those forms hidden not through intention, but through scale. Depth, pressure, distance, and darkness combine into a barrier more difficult to cross than most landscapes on Earth. Even now, after satellites, sonar networks, and robotic exploration, large regions beneath the Pacific remain physically more remote than the surface of the moon was to earlier generations. Beneath the storms and currents of the Devil's Sea, entire sections of the planet still wait in complete obscurity beneath kilometers of cold-moving water. In most parts of the world ocean, danger arrives with some form of warning. Storm systems appear first on distant horizons or modern satellite imagery. Currents become familiar through repeated crossings. Hazardous reefs are marked onto charts generation after generation until their locations become routine knowledge. Human navigation depends not on eliminating risk entirely, but on surrounding it with layers of prediction, preparation, and response. The Devil's Sea unsettles that structure in a different way. What distinguishes the corridor psychologically is not merely that it is dangerous, but that several forms of danger overlap there simultaneously, while reducing the normal margins through which humans usually maintain control. A typhoon in open ocean is destructive, yet modern forecasting can often track its movement days before impact. Mariners alter routes, delay departures, or seek protected waters. The danger remains immense, but it behaves within systems humans increasingly understand. An underwater volcanic eruption behaves differently. Beneath the Devil's Sea, geological activity may alter water conditions with little or no visible surface indication beforehand. Gas release can reduce buoyancy abruptly. Submarine earthquakes may occur without warning to vessels directly overhead. Hydrothermal systems shift beneath darkness, beyond ordinary observation. The ocean itself can change character faster than surface navigation systems are designed to anticipate. Even the act of orientation becomes less certain here. For centuries, sailors crossing this corridor recorded compass behavior that seemed inconsistent with expectation. Modern geological understanding now explains much of this through magnetic irregularities associated with volcanic rock formations and tectonic complexity beneath the sea floor. Yet explanation does not remove the practical consequence. Navigation systems become less reliable precisely where environmental instability is already elevated. Depth intensifies the psychological effect further. In shallower seas, wreckage can often be recovered. Accident sites become accessible to divers, investigators, and salvage operations. Physical remains provide closure, data, and reconstruction. Inside the Devil's Sea, many regions descend thousands of meters into trenches and abyssal terrain beyond ordinary recovery capability. When something disappears there, the ocean frequently retains the evidence beyond practical human reach. Distance compounds everything else. Rescue operations depend heavily on time. The farther a vessel lies from ports, aircraft support, and nearby traffic corridors, the narrower the survival window becomes after catastrophe occurs. Across large sections of the Devil's Sea, help remains physically distant, even under ideal conditions. In safety engineering, there exists a principle known as defense in depth. The concept is simple. Secure systems survive because they contain multiple independent layers of protection. If one safeguard fails, another compensates. Navigation errors are corrected by charts. Mechanical failures are mitigated through redundancy. Weather hazards are managed through forecasting and communication networks. The Devil's Sea systematically weakens many of those protective layers simultaneously. Navigation becomes less dependable. Geological conditions remain unstable beneath the surface. Weather intensifies rapidly beyond ordinary statistical expectation. Rescue distances expand. Recovery becomes limited by depth. Environmental conditions interact unpredictably rather than remaining isolated hazards. None of this requires supernatural interpretation. The region feels psychologically different because the ordinary architecture of human safety loses stability there. The systems people depend upon to create predictability retain less authority over the environment. That reality shaped human behavior long before scientific terminology existed to describe it. Fishing rituals, seasonal taboos, departure ceremonies, and inherited maritime stories emerged partly as cultural mechanisms for transmitting risk across generations. Communities lacking satellite forecasting or tectonic science still recognized patterns through observation. Certain seasons brought greater danger. Certain waters behaved unpredictably. Certain crossings demanded caution beyond ordinary voyages. Over time, those observations became encoded into ritual language because ritual preserved memory reliably within seafaring cultures. Fear itself became functional, not irrational panic, but a durable warning system carried socially across centuries. The emotional atmosphere surrounding the Devil's Sea, therefore, arises from something deeply grounded in reality. Humans sense vulnerability most strongly in environments where prediction weakens and response time collapses. Here, the ocean reduces many of the ordinary distances between normal conditions and catastrophe. Beneath the storms, currents, and volcanic structures lies a place where natural forces converge faster than human systems comfortably accommodate, leaving generations of sailors with the same enduring understanding that this water permits very little margin for error. Modern shipping still crosses the Devil's Sea every day. Cargo vessels moving between Japan, the Philippines, Taiwan, and the wider Pacific continue passing through the same corridor that older sailors once approached with ritual caution and incomplete charts. Oil tankers, research ships, fishing fleets, and container carriers all move through these waters as part of the economic bloodstream of the Pacific. The region was never abandoned. Human dependence on maritime trade became too large for avoidance to remain practical. What changed was the technology guiding those ships. For centuries, navigation depended on magnetic compasses, celestial observation, radio bearings, and dead reckoning. A vessel caught in storm conditions with unreliable bearings could drift gradually into open ocean without realizing how far it had wandered from its intended course. Modern satellite navigation transformed that relationship almost completely. GPS systems now allow ships to determine position with remarkable precision, independent of the shifting magnetic conditions beneath the seafloor. The old fear of compass error no longer dominates modern navigation in the way it once did. Still, the corridor has not become entirely predictable. Mariners operating in parts of the Devil's Sea occasionally report temporary irregularities in satellite positioning and communications. Most are brief and manageable, usually linked to atmospheric interference, equipment limitations, or electromagnetic disturbances that remain under study. Modern vessels possess multiple backup systems capable of compensating for short interruptions, yet the reports persist, often enough to remind navigators that the environment below the hull remains unusually dynamic. Weather forecasting has advanced even more dramatically. Typhoons that once appeared from distant haze with little warning are now monitored continuously by satellites, ocean buoys, reconnaissance aircraft, and atmospheric models processing enormous streams of data. Routing centers guide vessels around developing systems days before dangerous conditions emerge. Captains receive constant updates about wave height, wind speed, sea surface temperature, and projected storm movement across the Pacific Basin. Yet forecasting can only monitor hazards visible from above. No technology currently exists that can reliably warn a vessel about an imminent methane blowout beneath the seafloor. Submarine volcanic eruptions may begin far below the surface with little detectable evidence overhead. Sudden water density changes, underwater landslides, or localized geological disturbances can develop faster than any warning system can meaningfully respond. Scientific organizations continue trying to narrow that uncertainty. The Japan Agency for Marine Earth Science and Technology maintains monitoring equipment across portions of the region. Deep sea seismometers record tectonic movement beneath the corridor. Hydrophones listen for underwater eruptions and seismic fractures. Temperature sensors monitor hydrothermal activity rising from volcanic systems below the seafloor. Satellites observe subtle variations in sea surface conditions that may correspond to geological disturbances underneath. Even so, the coverage remains incomplete. The Devil's Sea spans an enormous and geologically complicated section of the Pacific. Large areas remain beyond continuous real-time observation. Events unfolding in deep water may propagate upward faster than human systems can detect, analyze, and communicate them across the distances involved. Search and rescue capability has improved enormously since the middle of the 20th century. The Japan Coast Guard patrols the corridor actively using aircraft, satellite communication, distress beacons, and vessel tracking systems based on automatic identification system transmissions. Modern ships are also substantially larger and more structurally resilient than many commercial vessels lost during the early post-war decades. But vessel size alone cannot eliminate convergence. A single hazard is often survivable. Modern ships can withstand severe storms, navigate strong currents, and reroute around typhoons. The Devil's Sea remains unusual because several dangerous systems can overlap within the same moment and place. Geological instability, extreme weather, deep ocean isolation, and rapidly changing surface conditions continue interacting in ways that reduce the ordinary safety margins modern navigation depends upon. So ships still cross the corridor every day beneath satellite guidance and digital charts, while far below them, the Pacific continues moving through darkness with the same restless force that shaped these waters long before human beings first sailed across them. Far below the shipping corridors and storm systems of the Pacific, the ocean continues operating according to rules that human beings only partially understand. The Devil's Sea reveals this more clearly than most places on Earth because it is one of the rare regions where the hidden machinery of the deep ocean rises close enough to the surface for people to encounter it directly. Beneath these waters, tectonic movement, volcanic heat, methane chemistry, biological adaptation, and atmospheric instability all overlap within the same narrow geography, turning the corridor into something larger than a maritime mystery. It becomes a visible cross-section of the planet itself. The ocean dominates Earth in both scale and influence. It covers roughly 71% of the surface and contains approximately 97% of all water on the planet. Continents, when viewed from orbit, appear almost secondary beside the uninterrupted blue mass surrounding them. Yet despite that scale, the deep ocean remains among the least explored environments humanity has ever attempted to study. More detailed maps exist for portions of Mars than for vast areas of the Pacific abyss. The Devil's Sea exists at the point where that hidden world begins pressing upward into ordinary human experience. Most deep ocean processes unfold silently and invisibly beneath thousands of meters of water. Hydrothermal systems circulate through fractured crust far below sunlight. Methane accumulates inside frozen crystalline structures buried beneath sediment. Tectonic plates shift gradually over centuries before releasing stored strain in moments of violent rupture. Entire ecosystems live and evolve in darkness without any connection to the rhythms of the surface world above them. In most regions of Earth, these processes remain distant from human activity. Here, they do not. The unusual character of the Devil's Sea comes from the way deep planetary systems repeatedly intersect with the navigable ocean surface. Geological disturbances reshape current behavior. Volcanic activity alters water chemistry. Seafloor topography redirects wave energy upward through the water column. Heat rising from below contributes subtly to atmospheric instability above. The boundary between the visible ocean and the hidden ocean becomes thinner here than in most other places. For scientists, this has made the region deeply important, far beyond its reputation in folklore or maritime history. Research conducted in and around the Devil's Sea has contributed to broader understanding of tectonic boundaries and subduction systems, helping geologists model how plates deform and release energy beneath ocean basins. Studies of hydrothermal vent ecosystems transformed biology by demonstrating that life does not require sunlight as its primary energy source. Chemosynthetic organisms surviving through chemical reactions alone expanded scientific understanding of where life might exist, not only on Earth, but potentially beneath the icy oceans of distant moons orbiting other planets. Methane hydrate research in this region has become equally significant. The frozen methane deposits beneath ocean sediments represent one of the largest carbon reservoirs on Earth. Scientists studying how these hydrates destabilize during warming seismic disturbance, or volcanic activity are also studying mechanisms tied directly to long-term climate behavior across the planet. A process unfolding in darkness beneath the Devil's Sea may ultimately influence atmospheric systems thousands of kilometers away. Even the currents flowing through the corridor contribute to broader oceanographic knowledge. The interaction between the Kuroshio Current, deep topography, volcanic heat, and atmospheric circulation has helped researchers understand how energy moves between ocean layers and how regional instability can influence weather patterns across the Pacific Basin. All of this leads toward a quieter realization. The ocean is not a passive backdrop surrounding human civilization. It is an active geological, chemical, and biological engine operating continuously across planetary scales of depth and time. The Devil's Sea simply makes that activity more visible than most places do. For centuries, sailors crossing these waters encountered the surface expressions of systems too vast and too deep for them to see directly. Modern science has illuminated part of that darkness, yet the region still reminds us how much of the living planet continues moving beyond the edge of ordinary human observation. For decades, the Bermuda Triangle occupied a strange position in popular imagination, suspended somewhere between maritime folklore, paranormal speculation, and cultural mythology. Its borders became familiar even to people who had never looked at a nautical chart. The names alone carried recognition: Florida, Bermuda, Puerto Rico, places connected by tourism, aviation, shipping, and the immense reach of American media. Stories emerging from that region traveled quickly through magazines, television documentaries, paperback books, and late-night radio. Entire generations grew up hearing about vanished aircraft and missing ships in the Atlantic, without ever questioning how those stories had been assembled in the first place. The Devil's Sea never received that treatment. Its records remain scattered through Japanese maritime archives, scientific reports, fishing histories, and regional accounts that rarely crossed into English-language publishing. The corridor existed far from Western population centers and recreational shipping routes. Few European or American vessels crossed those waters regularly enough for the region to become culturally familiar outside East Asia. The ocean itself remained the same, but the stories attached to it traveled through entirely different systems of language, geography, and attention. When researchers began examining the Bermuda Triangle systematically, the picture changed substantially. Organizations including the National Oceanic and Atmospheric Administration and the United States Coast Guard found no statistically unusual pattern of disappearances relative to the enormous volume of traffic crossing the Atlantic corridor. Hurricanes, navigational mistakes, mechanical failure, human error, and ordinary maritime risk explain the overwhelming majority of incidents associated with the Triangle's legend. The region is certainly capable of dangerous weather, especially before modern forecasting and satellite navigation. Yet its risks belong largely to categories that oceanographers and navigators understand well. Its geology is comparatively quiet. The Bermuda Triangle does not sit above one of Earth's major tectonic collision zones. It lacks active submarine volcanic systems capable of rapidly altering sea surface conditions. Claims of abnormal magnetic behavior in the Atlantic corridor have largely dissolved under careful measurement, revealing compass variation patterns that are normal, charted, and predictable. The Gulf Stream remains powerful, but its behavior is extensively studied and integrated into modern navigation models. The Devil's Sea presents a profoundly different scientific picture. Here, magnetic anomalies are real and geologically explainable, produced by constantly shifting volcanic rock beneath the sea floor. Active submarine volcanoes erupt within the corridor itself, releasing heat, ash, and gases into the water column. Methane hydrate deposits lie buried beneath deep sediments, capable of destabilizing during tectonic or volcanic disturbance. One of the planet's most active subduction systems moves directly underneath the region, generating earthquakes, tsunamis, and constant geological strain. Above it all, the Kuroshio Current interacts with typhoon systems and complex seafloor topography to create unusually unstable atmospheric and oceanic conditions. Even the depth changes the equation. Wreckage lost in portions of the Devil's Sea may descend into trenches or abyssal plains thousands of meters below the surface, beyond the reach of most recovery technology for much of modern history. Currents can disperse floating debris rapidly into the wider Pacific, leaving little trace behind. The corridor removes evidence almost as efficiently as it removes ships. This does not transform the Devil's Sea into something supernatural. It simply means the scientific basis for danger there is stronger, broader, and more measurable than the mythology surrounding the Bermuda Triangle ever suggested for the Atlantic. The comparison is not really about mystery versus explanation. Both places are explainable. The difference lies in the underlying mechanics driving the danger itself. The Bermuda Triangle became famous because it existed close to American shores during a cultural moment fascinated by unexplained phenomena, and because writers with access to global publishing networks chose to elevate its stories into international mythology. The Devil's Sea remained comparatively obscure because its evidence existed mostly in another language, another media landscape, and another side of the Pacific. Meanwhile, the ocean continued operating without concern for which stories became famous and which remained hidden inside regional memory, scientific archives, and the deep water itself. Long after the storms pass and the scientific reports are archived, what remains most permanent about the Devil's Sea is not the mythology surrounding it, but the absence carried by the people left behind on shore. Ships disappear in records as coordinates, dates, and vessel names, yet every line in a maritime archive once belonged to living routines interrupted without warning. Someone prepared equipment before dawn. Someone packed clothing for a journey expected to end in return. Someone stood on a harbor wall, watching a vessel diminish into distance beneath an ordinary sky, unaware that the separation would become permanent. Among the most remembered losses were the researchers aboard the Kaio Maru No. 5 in the early 1950s. They were not thrill-seekers chasing folklore. They were scientists, technicians, sailors, and observers sent to study the eruption of an underwater volcano whose activity had become impossible for Japan to ignore. Their mission belonged to a nation rebuilding itself after war, trying to understand the geological forces shaping its surrounding waters. The ship sailed toward knowledge. Weeks later, fragments of wreckage were recovered from the sea, and the ocean closed again above whatever remained below. The fishermen lost across earlier centuries left fewer written records, but their absence shaped coastal communities just as deeply. Along the Izu Peninsula and surrounding islands, departures into dangerous waters gradually accumulated layers of ritual. Families prayed at shrines before voyages. Offerings were left for protection. Departure seasons were chosen carefully around storms, currents, and remembered patterns of loss passed through generations. These customs carried spiritual meaning, yet beneath them lived practical memory, encoded observations preserved long before meteorology or seafloor mapping existed. Ritual became a way of carrying accumulated grief without allowing it to dissolve completely into silence. Maritime loss possesses a particular emotional shape, unlike death on land. On land, grief often gathers around physical places. Graves are visited, names are carved into stone. There is somewhere to stand, somewhere the living can return to repeatedly across years and generations. The ocean rarely permits that continuity. A ship sinking into deep water leaves no visible scar on the surface. The coordinates themselves drift within storms, currents, and immense distances. Even when approximate locations are known, the wreckage may lie thousands of meters below the reach of ordinary human access. In the Devil's Sea, that separation becomes even more complete. Many vessels lost in the corridor almost certainly rest upon abyssal plains or fractured volcanic slopes buried beneath darkness so deep that sunlight has never entered it. Steel structures collapse slowly under pressure and corrosion, while sediment settles quietly across decks and railings. Currents move above them. Geological systems continue shifting beneath them. In time, the wreckage itself becomes incorporated into the ocean floor, no longer entirely distinct from the environment that consumed it. Human beings struggle with this kind of disappearance because memory prefers boundaries and locations. People search instinctively for places where grief can settle. A shoreline, a marker, a recovered object, anything that transforms absence into something tangible enough to touch. The deep ocean resists that instinct completely. It keeps distance between the living and the lost with almost planetary finality. Yet perhaps this is also part of what gives the sea its enduring emotional weight within human history. For all our technology, charts, satellites, and scientific understanding, the ocean still retains the ability to remove things beyond recovery and beyond witness. It does not do so with intention or cruelty. Currents continue moving. Tectonic plates continue shifting. Storms gather and disperse according to physical laws older than humanity itself. The Devil's Sea simply reveals this more openly than most places. Beneath its surface, the unrecovered remain held inside a world that continues existing whether human beings observe it or not, vast and dark and patient beyond the edge of memory, carried on shore. Far below the shipping lanes and weather systems of the Western Pacific, the Devil's Sea continues its slow work in darkness that predates humanity itself. Long before fishing villages appeared on the Japanese coast, before the first compass crossed open water, before any language existed to name this region, tectonic plates were already grinding beneath the ocean floor. Volcanoes were already rising and collapsing beneath kilometers of water. Hydrothermal vents were already pouring mineral-rich heat into the abyss, while pale organisms clustered around them in complete isolation from sunlight. Nothing described throughout this journey began with human discovery. The Kuroshio Current had already been flowing northward beside the Japanese archipelago for thousands of years before the first written records appeared. When the last ice age loosened its grip on the planet and melting glaciers reshaped coastlines across the Pacific Basin, the current adjusted and continued. Warm water still streamed through the corridor with enormous force, carrying heat, nutrients, storms, and drifting life across distances larger than entire countries. Human civilization emerged beside it only recently, in geological terms, learning gradually how to survive near a system vastly older and larger than itself. Beneath that current, the subduction boundaries of the Pacific continued operating across spans of time almost impossible to picture clearly. For tens of millions of years, oceanic crust has descended beneath the edge of Asia in cycles of pressure, melting, uplift, and rupture. Those forces built the islands of Japan from volcanic stone, lifted slowly from the sea. They shaped trenches descending deeper than Mount Everest is tall. They produced earthquakes, hydrothermal fields, methane deposits, and entire chains of submarine volcanoes hidden beneath open water. The Devil's Sea is not separate from those processes. It is one visible expression of a planetary engine still actively reshaping the Earth beneath the ocean. Even the living systems below belong to timelines far older than humanity. Around hydrothermal vents on the sea floor, tube worms sway within mineral-rich currents beside bacteria that draw energy not from sunlight, but from chemistry itself. These extremophile communities resemble some of the oldest ecosystems ever to exist on Earth. Their distant ancestors lived more than 3 billion years ago, when complex plants and animals had not yet appeared and the continents themselves looked entirely different. Life endured there in darkness long before forests, mammals, or human beings existed above the surface. Against those scales, recorded human history becomes astonishingly brief. Civilization, agriculture, cities, written language, navigation, science, all of it occupies only a narrow fragment of time beside the geological age of the Pacific. Entire empires rise and disappear more quickly than ocean trenches form. Human generations pass like weather over water that remembers ice ages. Perhaps this is what gives the Devil's Sea its particular emotional gravity. The fear surrounding the region is scientifically grounded, built from genuine hazards shaped by geology, weather, pressure, current, and depth. Yet, beneath that fear exists another sensation, quieter and more difficult to describe. It is the feeling of encountering a system that does not recognize humanity as central to its existence. The ocean does not organize itself around human survival, memory, or understanding. It simply continues operating according to physical laws older than every story ever told about it. The sea does not know that sailors feared it. It does not know that ships vanished above its trenches, or that researchers lowered instruments into its darkness, searching for answers. It does not know that names like Devil's Sea or Dragon's Triangle were ever spoken aloud. It continues because continuation is what oceans do. Currents flow, plates descend, vents release heat into black water. Creatures without eyes drift through darkness beneath storms they will never witness from below. Somewhere along the seafloor tonight, an organism no human has ever seen is moving slowly through mineral clouds in a world untouched by sunlight, living an entire existence completely unaware that another world exists above it at all. That is the Devil's Sea. Ancient and indifferent beneath the Pacific sky, and now its hidden systems no longer belong entirely to mystery.